Welcome to the 10 truths of distributed system designs. We just saw the top scoring sessions, so I have a small exercise for you guys. So please count along your row and figure out where the fifth person is sitting, because that's the only person who can give less than 5 stars. So if only every fifth person gives 4 stars, we will get the top score for the session. So if you do your part, I will do my part, and we'll have a good fun for the next 3 hours. I think we have about 99 slides or so, so no lack of content. So, quick recap, quick trip back in history. I've had a knack or a thing for integration patterns for a very long time, since my early years. And as you can see, I wasn't just interested in how things communicate with one another. Obviously, I was already interested in loosely coupled systems, because that thing isn't plugged into anywhere. But more seriously, a lot of you guys know that a long time ago, so not that long after this picture actually, I wrote a book with Bobby Wolf called Enterprise Integration Patterns. And for about 20 years, my publisher has been nagging me. It's like, hey, you know, you're going to ever finish the volume 2? Some of you guys might know there's a sort of work in progress conversation patterns on the website. And sort of about 20 years later, I went back to my publisher. So that is now, right? That was 2003, 2004. So I went back to the publisher and say, hey, I think I have a bunch of new ideas that I want to talk about that didn't make it into enterprise integration patterns, but that are germane to distributed system design. So the publisher said, oh, that's fantastic. I only waited 20 years for this. So this is brand new. First time I'm giving this talk means 2 things, right? Never before seen content, so that's great. Remember the 5 stars. Also means not all the diagrams are as pretty as they will ultimately be, and some sections are a little bit shorter than others, right? So basically you're getting sort of the 0.9 version of the talk, but as we all know about agility and the cost of delay, right? We want to have things early, so that's what you're getting here. So a little bit of a special treat. And many of you guys know, like, writing is sort of my form of therapy. So I've been, writing further on architecture, cloud platforms. We have tomorrow keynote, and I think we'll have actually some books here for you guys tomorrow. But today it is sort of travel back in time, almost 20 years, 2003, enterprise integration patterns, and we'll talk about distributed systems. So when you hear the title 10 Truths, probably this thing comes to your mind, right? There's these famous 8 fallacies, right, by the famous Sun folks, where they said, hey, distributed computing has these like inherent problems that people don't think about. And people think like, oh, there's no latency. They think the network is reliable. They think it's homogeneous, all these kind of things. So well understood. Now, the downside with fallacies is it makes it a little bit sad when you write distributed systems, right? Because all these fallacies, all these things you can't be doing wrong. And so I thought like the fallacies are a little bit negative in a way, because it sort of pokes the finger at all the mistakes we make. So why not turn this into positive and talk about the 10 truths? And of course, I didn't take the same ones, because there's plenty of cool and new stuff coming along. And a lot of this, again, my own time travel, right? 20 years ago, we wrote enterprise integration patterns. 2 years ago, I started working at the AWS serverless team, just left that like a month ago or so. So I learned a lot more about operational aspects, scalability, and I realized the patterns are still super relevant, so 20-year time span, but that there's a whole other world to this which deals with all the operational aspects. So what you're getting here has sort of been 20 years in the making, so not only my publisher made fun of it, but it's really having thought about these patterns 20 years ago, and now we're in the cloud, we're serverless, we're highly scalable, we're automated, right? Understanding that there's more to talk about distributed systems than maybe 5 or 10 years ago. And with that, we have the 10 truths, and you don't need to memorize them all, because we'll go through them one by one. And you'll see we'll cover a lot of topics that have to do with coupling, a lot of things that have to do with control flow and flow controls and retries and those kind of things. A lot of the good stuff that we need to deal with when we build distributed systems, and particularly if we build distributed systems in the cloud, perhaps things like serverless, things like Kafka, like all the cool kind of stuff that we have today. So with that quick recap, where did the story start, right? The story started with asynchronous messaging, right? And the nice thing I always say is about asynchronous messaging, it's relatively easily broken down how asynchronous messaging works. It's sort of the simplest possible interaction style. And I'm guessing I probably was actually here around 2004 or so talking about enterprise integration patterns and laying out some of these basics. So for you guys who have been there, apologies for the slight rerun. Otherwise, a quick catch up from 20 years ago. What do we need to do to make a messaging solution, right? We need to transfer messages from A to B. There's no way around that. We need to design the messages, right? There needs to be message content. Is this a command, an event, an update, kind of notification, a document, right? It needs to have some sort of structure. It needs to find its way because we have channels and routers, right? We have sort of different ways to move the messages from A to B. And we also need to maybe transform messages because a lot of this came out of the context of integration where you don't have full control over the endpoints, right? So one endpoint might want to things in a different format than the other one. So the best thing you can do is put a transformation into the middle. Now, the world of messaging and sort of more tree document-oriented data structures is generally different than the object-oriented world inside the applications. So you have things like serialization, marshalling, unmarshalling, transforming or expanding references, all that kind of stuff you have to do. And largely, you're building a fairly dynamic system. So you do want to know, I got to get my clicker here, you do need to kind of take care of, we would say, observability these days, right? You need to take care of understanding what's actually going on in your system. And we'll talk about this later a little bit. If you build something loosely coupled, the reason you make it loosely coupled is that it's more easily changeable, right? Change doesn't propagate, but that also means that your system is constantly evolving, right? Otherwise, you don't need loose coupling. But that also means that your system is changing all the time. So it's a very good idea to have systems management, monitoring, observability, so you actually know the current state that your system has. Well, and then, because those are the things that you need to put together to make a good messaging solution, right? This became the enterprise integration patterns, and this is essentially the 6 core chapters of the book, interspersed with chapters about running examples, like large examples, and a long example as an introduction, and that is then largely 700 pages, summarized here as the pattern language. In hindsight, in one way, we got a little bit lucky with the book because we got some things right without really kind of sort of knowing about it or thinking about very carefully. So a few things we were lucky to get right is the icons, right? The little Gregograms. People really latched onto those, and we'll see a lot more of them later. And also what we probably got right is that we didn't just make a long list of patterns. We didn't just say, like, here's pattern 1 and here's pattern 65, but we really defined a language that has a structure, that has a grammar, it has groupings, things are sort of chronologically lined up. Again, this wasn't something where we had divine foresight, right? It just sort of kind of happened, but in hindsight, that turned out to be a relatively good idea, right? So these are the icons, the Gregograms. There's always a going joke. Scatter Gather didn't used to have one, so I made a new icon for it. So if you look on the website, it still looks a little bit like it's from 2003. It has like sort of this early 2000s look to it, but I still blog on it. So I recently posted quite a few updates about serverless as well as about some of the coupling stories we'll hear about today. And I actually made one of the missing icons, right? And the nice thing about these messaging solutions and these icons was that you can easily compose this, right? It's sort of this pipes and filters pattern, because messaging is, you send a message, you receive a message. It's very easy to string these things together, and the visual language affords the same thing. And many tooling, right? This is, sometimes Bobby and I get blamed for sort of having caused the ESB, and I always say it wasn't the fault of the patterns, it was more the fault of the teams who wanted to own everything integration, but this is what made its way into the ESB and into the integration tooling. People using this pattern language, describing their solution as, hey, I have a splitter, and then I have another splitter, I have a transformer, I have an aggregator, I have a filter, right? That's how people will speak, and that's really the purpose of the patterns. Right? There shouldn't be abstract things sort of painted on the wall. The patterns should be common words that you use to describe your solutions more precisely and more densely, right? And other people know what you meant, and you can do that in words, right? And you can also do this in diagrams, right? You see these kind of pictures behind it. So that's kind of the story of the patterns. And one thing we realized, so this is the integration chef. Some people might recognize this is also very old. I think this is made from TIBCO Process Manager in the early 2000s, where why is integration so important, right? Basically, what enterprise integration patterns has done is most people talked about the boxes, and then Bobby and I started talking about the lines, right? Like, what is in between the boxes? Is it a publish subscribe channel? Is it a point-to-point channel? Is there filtering? Is this an idempotent receiver? Is there a translator, right? We started talking sort of what's between the boxes, and one of the main motivations was that how you put together your system actually largely defines its operational qualities, right? How you put things together is in the end, just like in the restaurant, right? Good ingredients help, but in the end, it's the chef that defines the quality of the meal because it's how you put it together. And the same thing is true for architecture, right? Starting with good ingredients is helpful, but as an architect, you're still tasked with putting it together in a good way. So that's all we're going to talk about today. It's like we don't talk about the little boxes, right? We all assume that's well done. We saw all the other sessions that teach you about how to make beautiful boxes. Today it's all about cooking in a way, right? It's all about being the chef. It's like, how do we put these boxes together, and what do we need to keep in mind when we have those? So here we start with the first truth, right? And that is, it always starts with two boxes and a line, but it never ends there, because the messaging style is deceivingly simple, right? It's just like, hey, you just need to send a message from left to right. That is the strength of the asynchronous messaging style, but it's also sort of belies its own complexity, right? Because there's a lot of questions that you need to answer, right? Like, what is actually A and B? Is B the instance of a system where there could be multiple of, or is B the entire system? How does A even know to address B? Does B have the name B, or is this something else, right? Is this synchronous or more likely asynchronous? Is the arrow depicting the control flow or the data flow? As we'll see later, that makes a massive difference. And what is the data shape like? Do we have data types? Is this wire format? Is this protobufs, right? Is this Afro? Are there schemas? Are there not schemas? Do I need to authenticate? What if the message isn't delivered? Do I have a timeout? Do I have a retry? Do I limit the rate, right? Can B take as many messages as A ever wants to send, or do we need to rate limit? So very quickly, right, a slew of questions opens up. And I often use this, I flicked one too fast here. Does it go back? There we go. This is one example I often give where I say RPC is a dangerous illusion, because RPC tries to tell you that a remote call is similar to a local call. They said, it's like a procedure call, but it just sort of happens to be remote. And I find that dangerous in a way because it makes you forget about all these kind of things, right? A remote call, whether it's synchronous RPC style or whether it's asynchronous messaging style, is fundamentally different. It makes your system scalable and resilient and also the other cool stuff, right? But it is a completely different pair of shoes, and that's why we need to pay attention to that seemingly simple arrow, because in the end, that is not actually as simple. So coming back a little bit to messaging, right? We already said like the patterns, right? This happens, on the basis of messaging. Why is messaging interesting? Yeah, might be a tiny bit biased, right? But honestly, I think messaging has distinct advantages, right? The first part is the simplicity of it. All right, there's a channel, there's a message, there's a sender and a receiver, right? That's to it. And it's actually, in a way, more interesting what it doesn't have. Like, it doesn't have a call stack. It doesn't have a return statement, right? It's most things are taken away. If A and B want to communicate somehow, you probably need to send some data from A to B, unless you maybe just want to have a ping. Fair enough, right? Then you have a very small or empty message, but like somehow they need to communicate. And this is the simplest way in which they can possibly communicate, because they don't make any other assumptions besides just like, hey, here's some stuff for you. Now, the nice thing is, by having a logical channel, things become location independent, and that is easy to do, right? You send the message to the channel, and you don't really care so much about who's receiving from there, right? Nice form of decoupling. We'll talk more about that, right? And it's quick because it's asynchronous, right? You can just pump these messages into the channel, because generally this channel has a queuing property. And we'll talk a lot more about this control flow and pushing and pulling messages and how queues behave and shape traffic. So the beauty of messaging is largely the simplicity of it, like what it does not have. It has nothing else, but here's a piece of data. Please get this to the other side ultimately. And that is really that. You can't really make anything much simpler than that to make two systems talk to each other. Well, and that gives us some nice benefits, right? It's asynchronous, so we have temporal decoupling, right? If B is slow in consuming things, A can still pipe the messages into the asynchronous channel because it buffers, it queues, right? It's very easy for B to consume messages at its favorite rate, right? It throttles, and we'll talk more about that later. It's much easier to tune the system for a steady processing rate. Like if there's a queue, when I say like, okay, the maximum at which I read this queue is 100 TPS or 1000 TPS, whatever it might be, it's much easier to tune a system for that than having crazy wild spikes on the system where sometimes it's, five messages per second, and sometimes it's, 5,000 or 50,000 or 500,000. So you can throttle, and it makes it much easier to tune the system because you have that kind of decoupling. Also, retries up to a certain extent are hidden in this, right? Because there's no guarantee of latency here. Nobody's waiting for the message. So if it takes longer, the network is unreliable, disconnected, you can retry, call this store and forward, right? You store the message until you can actually forward it. And basically, the model doesn't really have to change because of this, because the assumption is there that the message gets there ultimately. And because you talk to a channel and not to B, there could be a C or B star or something else in between A and B. A would never know. It just knows, it's just putting the letter in the mailbox, and sort of how many sorting or distribution centers this goes through, right? You don't need to deal with this because it is asynchronous, right? So the real life metaphor holds. The one maybe disadvantage, or the one thing to keep in mind, right? These can become very high throughput solutions because I said they're easily tunable to very high traffic, but they're often not the lowest latency, right? Because you get the queues, you get the retries. So this is throughput over latencies. Nice quote I like from old friend Clemens Masters, right? He always called this wider bridges, not faster cars. If we want to avoid, because up at Microsoft in Seattle, what is it, like the 520 or something, that's always congested across the lake. Like he always said, if we want to get the congestion out, we don't need faster cars, we need wider bridges. We need more throughput. Right? If the traffic jam is all Ferraris, or whether it's all, Volkswagen Golfs or whatever it is, right? That makes a little difference, but adding another lane, getting more throughput is really what you're after. So these solutions are like that. They're oriented towards high throughput. So it's amazing how this very, very simple thing can give us these nice properties, right? Like the simplicity of taking stuff away suddenly pays off because we get all these nice properties, right? And this is probably a quote from 20 years ago, even, where I might have been here said the same thing, where he said, rather than RPC, which says, hey, don't worry about all this distributed stuff, it's just a procedure call, right? That's an illusion. Some people might say it's a lie. It works sometimes. I mean, we have gRPC now and other things, right? So if it's wrapped properly, you understand all the error modes, you have retry logic and all the other things, it can be made to work, right? No doubt about it. But fundamentally, there's like, hey, that's just another method call, don't worry about the distributed stuff. That can end up being a dangerous illusion, because things like latency, failures, inconsistent states between sender and receiver, right? You send the message, you never get a response, like, did it get processed, did it not get processed, you send it again, is it idempotent, right? But all this kind of stuff you don't have in a local call. So messaging says, okay, some of these things are inherent, so I'm not making any guarantees about latency, right? The message will get there, but you send two messages, they might get there at different times or in a different order, right? I'm not giving you these guarantees. I'm not wanting to give you this kind of illusion, because I know that ultimately this will not hold. So that's why I'm saying this is like an honest style. If you deal with distributed systems and the fallacies of the distributed computing, right? The fallacies of the network. This style doesn't pretend that those fallacies don't exist, right? It acknowledges it. So it acknowledges they might be heterogeneous, and acknowledges that the network might be unreliable. It acknowledges that there's latency. So I find that to be an honest style. Now, to be fair, it puts a bit more work on you, right? Making a method call and a call stack is super convenient, right? It's like you just call a method, it comes back right from there, it knows where it goes back to, it waits for the results, right? It's a very nice programming model. So this puts a little bit more effort, a little bit more work in your camp, right? But in return, you avoid these dangerous illusions, because you understand that you're working with a distributed system which has different properties than a local system. So the thing is, the asynchronous part is one of those harmless words, right? What does async in a way mean? Like synchronous, like synchro, comes from like clock timing, things happening at the same time. So something that is async, it means it's kind of a little bit out of order, right? It's not on the same clock, if you wish, right? So a harmless sounding word, we like this a lot, but in the end, it actually challenges our thinking quite a bit. And that is because we are used to building synchronous systems so much, right? And that's why threads, for example, are popular, right? Because you can do multiple things in parallel, but each of them kind of still lives in this, hey, I do one thing, I call something, I get the response. Now, since those 20 years, asynchronous programming styles have become more popular, right? And partly through JavaScript, and you have promises and completions and await statements. You have akka and reactive kind of programming styles. So there's a lot of folks found that actually this stuff makes a lot of sense for event-driven, asynchronous UI kind of things, right? So that is good for us, because it gets more of us used into this model of what I call programming without a call stack, because you do one thing and it kicks off something else, and the two run in parallel. It can still twist our brains a tiny bit, right? Because we're so used to that the model on the left is nice and orderly, right? This calls this calls this, right? And then it goes back the same way it works, and we can sort of think about one request at a time, right? There's a new order, this order needs to go here, needs to go there, and then when it's all finished, it comes back. But you also see the challenge already, right? If this is a distributed system, there's a lot of wait time. You can say, okay, I can do other things in this wait time. I can pause the thread. I can run different threads. I can do clever things about it. But fundamentally, if you look at a system where sort of 90% of the time spent, right, time running from top to bottom, right, where 90% of the time spent is waiting for other things, you're kind of wondering whether this is the highest throughput solution, right? Remember, we were after throughput. Waiting is sort of the antithesis of throughput, right? Things that are waiting are not processing messages or data, so they will reduce throughput. So the thing that kind of gets us a little bit is that in the asynchronous world, this is more like a pipeline, where like sort of one element is already being processed, it's in stage 2, the second one comes right after. So like in a way, all these things happen at the same time. There might be a short act right at the front, right? We said the message gets put on, and there's an acknowledgement that the message is actually on the channel, but then sort of things flow freely through there. Flowing freely is great for throughput, but flowing freely can also be a little bit harder for us to reason about these kind of systems. And Bobby and I have all sorts of funny stories where, wow, we've actually built a request-reply pattern once out of 2 message channels because we wanted a simple example of sending a message and getting a response. And we send messages as like, we were testing, we sent like foo comes back, we send foo again, foo comes back, everything is working. We send bar, foo comes back. Right? We said, how can this be, right? And then we said, well, let me try this again. So I put bar, and like bar comes back. Oh, it's working now, right? And then what we realized much later was there was a message stuck on the channel. So request and response was one message delayed, and if you always send the same test data, you never notice, right? And I laughed about it because it's like 2 guys writing a book about asynchronous messaging, and we're making sort of the dumbest mistake you can make, right? The message stuck on the channel, and we didn't notice. I said, on one hand, okay, good, we're writing this book, right, to help people not fall in the same trap, but it's kind of ironic, right? It's so easy to fall into this thing. You think you're just talking to something, it sends you an answer, but now there's stuff in between. There's channels, there could be messages on these channels, right? So that trips you up much more easily than you might think or you might like. So another way to characterize this, right, is in a way the synchronous, the sort of RPC, the procedure call-oriented model on the top, that tracks the state of this conversation in the endpoint, right? A knows that it's waiting for something from B. That's in a sort of local world, that's your call stack, right? Something goes onto the stack, it gets pushed on the parameters, the return address, right? That gets popped off when it returns. So there's data allocated there on behalf of the caller, right? The caller needs to know the state that it's waiting for something from B. And in a messaging model, that essentially goes away. The state is the little circle there that travels from left to right. So the state is in the message, A and B in the. So we're abstracting a little bit here, fair enough, right? But to get the purest version is neither A nor B carry any state of this conversation. It's where that little circle is, that's where the action is. The little yellow circle comes at B, B does something, sends another message. So there's no this tracking, right? And you can see that this is very, very efficient, right? You have the state completely in the message, and that message travels, and wherever that message goes, something happens. That's again where the throughput comes from, and we'll see more about this later. Now, maybe last one to sort of underline why messaging is so great. People, it's always good to, to quote people smarter than yourself. So Alan Kay definitely in this league. This is like a very old, I need to look at the date here. What does it say? 1998, okay? October 1998, that is older than enterprise integration patterns, where Alan Kay was basically having an email exchange with folks and said, hey, the core part of this, this is probably around small talk and early days of object-oriented systems, right? Remember design, this was after design patterns is from 1995. I think, actually. So this is around that time where people discuss object orientation. So he's saying messages is actually the big idea. Well, it's right here, small talk squeak, right? It's like, and then he goes Japanese, whatever else, right? But he's basically saying the idea of one thing sends another message, making that loosely coupled, a word we like a lot. That is actually the core idea. So there is something about messaging. Now, when anybody talks about distributed systems, like messaging or event-driven, whatever it may be, the next word they usually say is, oh, but it's got to be loosely coupled. So again, we can quote some folks there. There's a wisdom from David Orchard, like BA, like old days, smart guy. And he said, well, if you want things to be ultimately loosely coupled, right, why? How about not connecting them? They might not be doing anything useful, so that is the downside, right? So long story short, right, you will always have some coupling. Right? You will always have some dependencies between the system because the only way to do it is not to connect them, and ironically, you might still have coupling. Like two separate things might be running on their own clocks and making assumptions about each other, even though they're no longer actually connected. So you can even couple them if they're not connected. But if they're connected in any way, which is normally what we prefer in a distributed system, they will be coupled. So there's always something about coupling. And my definition of coupling is that it's a measure of independent variability, right? It's like how tightly is this coupled is if B changes, will A also have to change. It's about change propagation. And change can come in many forms, right? This can be a functional change, an API change. It can be a behavior change, right? B might be slower now than it used to be. It could be an availability change. B is not actually available now. B might be moving to another location. It's not where it used to be, right? Change comes in many flavors, and the question is, when that change happens on one side, does it necessitate a change on the other side? And the examples I just gave already hint at that is not a single dimension. You're not simply sort of coupled. Whenever you say, are things coupled or loosely coupled or tightly coupled, you pretty much have to state along which dimension. You know, things might be tightly coupled on the data types because you have, like, let's say JMS, right? In the old days we say, like, hey, you know, this is, you know, a known protocol, known APIs, so I have Java on both sides, so I'm technology coupled, I may be coupled to the data types and the data encoding, but I might be temporally and location decoupled. So I'm coupled on some things other. Versus you might be doing synchronous things with XML or JSON where you can say, hey, I'm not coupled on data types and data formats, but now I'm temporarily coupled. Or maybe I use an IP addresses, now I'm location coupled, right? This coupling thing isn't a single thing. There's many different dimensions on it, including some like order. Does one side assume things come in order, right? I just mentioned I worked on serverless in the cloud, so the high throughput systems, you know, happens all the time. People run things at low volume, and in low volume for like tests and stuff like that, or maybe low volume production even, things arrive in the same order in which they were sent, largely because the system hasn't had a need to scale out. So they make an assumption that things come in the order in which they were sent. When the system scales up, well, the traffic goes up and the system scales out, I should say more correctly, so now things get processed out of order. And that's when coupling comes important. Does this change propagate? Does now things getting out of order affect the other systems? Like, did they make an assumption about order? And if they did, you're ordering coupled. Right? These are things that we don't think about so easily, and those are the nastiest kind of bugs, right? Where things, duplicate messages out of order, stuff changes, like sort of unexpected change comes, and that change trickles through the system, right? And that's why we rightly so talk about coupling quite a bit, but the big fallacy I always see people fall into is people think coupling is sort of binary. Like when you hear people talk about, oh, this is tightly coupled and this is loosely coupled, it's like somebody flicked a switch. Totally not true, right? This is like shades of gray all the way down, and it's not a single dimension. Tightly coupled along which, or loosely coupled along what? So coupling has shades of gray. It has many shades of coupling. It has many dimensions of coupling. And I like pictures, I like diagrams, so I started putting some of these in different diagrams, like technology dependency, right? If you're interacting with a service and the implementers of the service decide to change their programming language, or they might be changing their processor architecture from something big endian to small endian, right? Like very nice stuff that can happen. Does that change trickle through? Do you need to know? Right? And if it's loosely coupled, then you don't need to know location, right? Something scales out, it moves or fails over, right? It moves from one availability zone to the other. Does the sender need to know? It's an intermediate we insert, right? Topology, the structure of the system looks different now. Do I need to know? Data types, right? How is this encoded? Does it distinguish small integers from large integers? How are floating point numbers encoded? Does it have long long integer numbers, maybe for financials, or does it not have, right? All these kind of things. Again, locally you never have to deal with this. Now these become interesting, and these are all different forms of dependency, like the conversation. What is expected to happen in which order is also coupling. It's a form of dependency. You guys might know my one famous article is the Starbucks does not use two-phase commit, right? I talk about how does the conversation at the coffee shop happen, and for example, are you allowed to pay before you get the bill? Right? Because you might know the coffee shop, you go there every day, right? So before they even tell you how much it is, are you allowed to pay, right? Those are rules around the interaction between the systems, making assumptions. And when the assumptions are there, and then the assumptions get broken, that's sort of when tight coupling raises its head, right? Where it's just boom. You always paid first and it sort of didn't matter. Now they changed the rule and said, oh, no, the till doesn't open until they actually given you the receipt, and they don't know where to put the money, and the conversation suddenly breaks because the change trickles through. Like I changed my behavior as a customer, and now it causes a problem with the conversation, the party that I'm talking to, right? I already mentioned order and temporal dependency. Do things to make assumptions about how long things take, and do things to make assumption that things happen in a certain order. All right, so this helps us really, put a different view on what coupling means, many different dimensions and many different shades of gray, right? It's not like magically coupled or decoupled, right? Some of them in more detail, right? Because there's some nuances, I said, between sort of having the topology. So common things that you would do is insert an intermediary, right? And you might do this for different reasons. You might need to filter out data. This often happens with logging or other things, maybe async fields that contain personal information, PII, that you want to take out. It might be that you want to track or monitor or log something. It might be that the data formats have changed, right? Many, many reasons that you would want to insert an intermediary. Or the other thing you do around topology is adding a new recipient. So that's why here I've distinguished the location, right? One thing just moving on its own, I distinguish from topology, right? If one thing moves from here to here, the graph still kind of looks the same. It's two pieces, just one of the two pieces happens to be in a different location. So that's what I call location decoupling or location dependency, depending which way you flip, right? But if the graph changes, right, there's more pieces either in order or more pieces where it goes to, I call that the topology. In the end, I don't think there's a need to sort of fight over the words, right? It's more like acknowledging that all these dimensions are there, and if somebody has better names for it, I'll be most happy to take those. All right, so here's like scaling out, right? These are slightly different, right? It's not like a new element comes, but there is more B's now. Remember, one of the first things with the two boxes on the lines we asked, is this B in its entirety, or is this one instance of B? So right here we are, right? B is more than one instance. There's multiple addresses, maybe route roaming, load balance, competing consumers, all these kind of things. And then I said, right, change also comes in operational flavors, right? And this is sort of outages, meaning B goes from available to unavailable, B goes slow, or B goes intermittently available, right? Sort of the brown or the really nasty kind of things. It kind of, whenever you look, it doesn't work, and if you show it to somebody, it does, right? We all know how this goes, right? So those are the nasty, actually they're harder to debug than straight out outages, right? Because straight out outages, you look what's down, things that sort of come and go or only happen under certain circumstances are notoriously difficult to debug. So these are all changes, right? And the question is always, if this happens to on one side, do I need to make a commensurate change on the other side? And that means they're coupled along this dimension. And if I don't need to make the change, if the change doesn't trickle through, then they're more loosely coupled along this dimension. So what we know here is like coupling is not a switch that you flick. We always, as computer scientists, we're always bound to think stuff is binary. I always say the only thing is binary is the way our processors work. The rest of the world is rarely actually binary. It's always gradations. And yes, the real world is also rarely one-dimensional. And so coupling is also not single-dimensional as we have seen. So why do we talk about this so much, right? Why do people run around and say, oh, everything must be loosely coupled? Well, this change propagation we can easily understand is cumbersome, right? If something happens over here and that change trickles through, if one small component, what was the saying, like a distributed system is the thing where a server that you didn't even know existed brings down your whole system, right? There's a clever saying like this, right? That is classic coupling, right? There's a thing way over here that you maybe didn't even know about, and that change propagates through and boom, everything falls on its face, right? So those are the things why we don't like generally tightly coupled systems, because they make more assumptions about each other. And if it's changes, let's say it's a functional change, right? It requires coordinated change. Right? If I change B, if it changes the data format, I also change A. That doesn't mean it's horrible, right? It's a little bit more work, but if I have automated testing, I have continuous integration, I have full control over A and B, maybe it's not the end of the world, right? I just need to coordinate these changes. And we'll come to this in just a tiny bit. The level of control you have very much determines how much coupling you can actually afford to have, because architects, right, we're not only chefs, we also know we're in the business of trade-offs. I always say it's easy to identify a poor architect. A poor architect is the person who speaks in this absolutes. Oh, everything must be loosely coupled. Oh, everything must be in a container. Everything must be here. Never do this, right? Those are easily spotted. Those are the poor architects, because the whole essence of architecture is that it's not ever or never black or white, 1 or 0. Is architects understand the trade-offs, right? We do this because we like these properties. We get some undesirable properties with it along the way, right? And we do X, Y, Z to minimize those impacts, right? That's how architects talk much more. We decided to do this because we wanted this. We understand the trade-off. We acknowledge that. That's how you identify much better architects. They don't talk in these they don't repeat these simple slogans. So what this means, right, as architects, we look at coupling, is tightly coupled systems are generally more efficient, right? If you use native data formats, you have no translation between them. You don't need to accommodate for big endian and small endian and encode numbers and marshalling, unmarshalling, and packaging and unpackaging, all these kind of things, right? To think about is, the strings, run length encoded or 0 terminated and have the UTF-8 characters, or is this all ASCII or whatever it is, right? It's like you fix it all, you do it once, you can build a very efficient implementation. It's just not gonna if one side changes its mind, right? Because it's a very tight contract. If everybody plays along and you fix everything, it is actually very efficient, right? So that is the trade-off that you make. And for these kind of systems, often you have better development, better IDE support. Well, think about the extreme thing, right? What is the most tightly coupled? Is one method calling another within a single JVM or a single process, right? It's same data type, same language, same location, synchronous, right? Like all the dimensions you go down, it's like coupled on all dimensions. But it's the nicest way to develop, right? I want to refactor, I change a parameter, I do this with a refactoring ID, I don't even think about it. I have fantastic tooling support, so this tight coupling is actually very handy, right? Like introduce variable, rename variable, introduce option parameter, change the order of parameters, boom, boom. All my IDE does this in a loosely coupled system, right? This can be a change order. If it's outsourced to a third-party company, they're like, oh, that's going to cost you, right? You're changing a field over here. We need to update all this stuff. We're busy. You wait like a month or two, and it will cost you some money, right? So those are the trade-offs. So it's not like tight coupling is bad. We do it all the time. It's just a matter of understanding where it's appropriate and where we should be cautious, right? And then, the story is essentially this is, exactly the opposite. Fewer assumptions about each other is you can make local changes because the changes don't propagate. Tends to be a little bit less efficient. I have famous stories from my insurance days where people built this application and we had built a sort of cloud runtime platform. They came to us, oh, this application is really resource intensive. Like always, I kind of wonder why you get bragging rights for building inefficient stuff, right? But it sort of happens to be say, oh, my application, it's like mine is like this big, right? It's like uses a lot of resources, right? And what turned out, what used all the resources, it was a relatively fine-grained application where somebody had decided that everything should communicate via XML. So 90% of what this application was doing was parsing XML and garbage collecting all the little strings and objects that I have, right? So that was loosely coupled overhead for no reason. This was a single application. They didn't need this independent variability, right? They could make a change over here when they made a change over there because they owned the whole thing. They knew everything. So this was, they paid a high price, in this case literally, because they paid for the infrastructure that it was running on for actually almost no benefit. All right, and again, you lose a little bit of developer of tool support. I warned earlier, right? It's a more honest style. It acknowledges the complexities of this distributed communication, things getting out of order, different data types, right? All this kind of stuff, latency, right? Partial availability, relocations, right? All these kind of things. So it makes you deal with more, and you have slightly less tool support generally for that, right? There's no like refactor, change my variable, introduce a parameter to my method, find all the callers of this method, right? Dependency graphs, all that stuff can be done, right? But it's a lot more legwork generally, right? And you see a lot of the API management tools and a lot of cloud providers making more and more of these tools, but it's kind of still in the making, right? I think in the last couple of years, observability is a word that we use much more, and I think that is very good that way, because without observability, we're really flying blind, but we can still see there's a lot of movement in that system, versus if you call a method and get a value back, there isn't so much movement in that system, right? We don't even think about it. So it is actually different. So here we come to some insight. I sometimes coin this the Gregor's law of distributed computing, that there isn't an easy answer for how much coupling you should have, right? I already made fun of the architects who said, oh, everything must be decoupled, right? That is wrong on two parts, because A, it's not decoupled or coupled, it's not binary, you already learned that. Well, actually wrong on three parts. So they assume it's binary, they assume it's a single dimension, and C, they're actually also wrong. Right? So you faulted them on three counts by saying a simple statement. So what we learn is that how much control you have over the endpoints is a big factor in how much coupling you can afford. And you might actually think that, logically you can relatively quickly think about this, right? It's like coupling isn't free. We just thought, right? So the design time cost is more difficult to design these systems. The runtime overhead I talked about, right? You don't want your system to be only parsing XML and garbage collecting. And then operational costs, right? What's actually going on in my system? Are my queues filling up? Do I need more consumers? Do I need to auto scale, right? It's just more moving parts. So the question we should ask is like, okay, right? Obviously, less coupling isn't always better. We pay a price, so we should think about it. So long time ago, this must be from 2004 or so, I wrote a blog post on enterpriseintegrationpatterns.com where I said, if you don't control, so if you loosen the coupling up, right, that is good because things can change independently. But if you don't observe what is happening, you're flying blind, right? Allowing things to change without observing how they change, and that is not a good idea. So in one way, you need to do, or in a way, you need to do one or the other, right? Either you do this, what is the Star Trek, I'm not so Star Trek savvy, the guy was like, make it so or something, right? It's like, Picard, is it, right? Whatever. I'm not in that camp, so, please educate me later. Basically, make it so, right? This is it. I decree this is what the system looks like. No changes allowed, right? That's the left-hand side. Then I don't need to look a lot what my system looks like because it looks exactly like what I said, in theory, right? On the right-hand side, I leave it more open. I allow change, but then I really need to see at what I have, because if I don't do that, I have no idea of the structure of my system. And then usually if I have no idea how my system is structured, the system will find a clever way to remind me of its structure. And that's usually when you have outages or other problems, and a change over here brings down everything else, and you have no idea how this happened, right? So you need one or the others, and this comes back to the chefs a little bit, right? The chefs are the ones who compose the solutions, and composing solutions isn't trivial, right? So good composers are few and far in between, and that makes good architects, right? You need to really think about how you put stuff together and how much flexibility you want to have. So there's an interesting question I'd like to ask people when I talk about distributed systems development, because remember, the old book is called Enterprise Integration Patterns. Now, we don't talk about EAI much anymore, so like let's be easy on the E, but basically we talked about integration. And then a lot of stuff I talk about now is distributed systems. So the thing is like, is that the same or is that two different things? So it's a little bit of a trick question. It is different things, but in a different way than what we thought. Technically, it's very similar. Like integration is inherently a distributed system. You know, if you call one method to another method, you don't call that integration. You call it integration because one system here, there's another system over there. They run in different locations, most likely, right? It is technically very similar. We use message queues, we use addressing. You know, we want to talk to another party, we need to know its address or its name. We have naming services, right? Technically, integration and distributed systems are actually very, very similar to the point of almost becoming indistinguishable. Yeah, I'm not a big fan of sort of splitting hairs over terminology. I would just say, by and large, it's the same thing technically. The stuff we work with is almost identical. Where the difference comes in is all in the way how it's done. You know, like another word we started using is socio-technical systems, right? I would be surprised if there is no talk about socio-technical systems at this event. I'm almost guaranteeing it is. So what we learn is that it's not just about the technical stuff, it's also about teams, level of control, timeline, and frequency. And then we get a read on like, a migration is something that is done one time, usually after the systems were built, most likely by a separate team. So that is not distributed system development because it's done very differently by different people at different points in time. Integration is sort of kind of in the middle, right? It gets done, but it's not pushed 100 times a day, right? We don't necessarily have the release cadence that we have for the applications in something that we call integration. And interestingly, it's also often done after the applications are built because some of them are commercial applications that we didn't even build. So that means it's also done by different teams and the level of control we have is fairly low. So now this also tells us that the people who run around everything must be loosely coupled, they often grew up in this environment. They grew up in integration. Maybe we even partly guilty with the integration patterns, even though the word coupling isn't that much in the book. Hence, we have this talk, right, as it took only 20 years to realize that. So we don't talk about coupling as much, but people come out of this environment, right? It's like integration. Right? I connect, Salesforce to SAP. I connect this existing homegrown system to something else. So the logic is, okay, because of that, the pre-existing systems, I have very little control over the rate of change, and this works both ways. If I need to change B because A changed, I can't get B to change because it's done by another vendor. So I put translators in the middle, right? I decouple, I do all these kind of things. And vice versa, if I don't want something to change, the vendor forces an update and actually makes a change whether I want to or not, right? It goes both ways. I have limited control, and that's where actually decoupling tends to pay off more, right? Because if A changes and B cannot change, I must decouple them because otherwise I can't get this thing to work. But in a distributed system, it's slightly different. This happens largely on the same cadence, right? I change something in A, the integration, I add a field, probably my routing or my message filter will also change because it uses that new field, right? I can make that change at the same time. Maybe B actually wants that new field, so I make A produce that field, right? And I push this all, I deploy this at the same time. It is the same team. So that's where the difference between integration and distributed system development is. Now, funnily, if you look at some of the cloud providers, this kind of tension plays out actually right in front of you. So I worked on event bridge pipes, so AWS's eventing serverless integration service, we actually called it. But the reality was that the changes I would make to event bridge, right? It's basic event router. It's not a lecture about event bridge. Event goes in, it does some filtering, routing, enterprise integration pattern stuff. it's much more likely that if I change my Lambda function or I change something in my application, that I want to change my event bridge configuration, because same logic, right? I have a new field, I want to filter or transform based on this field. So the rate of change now between my application and the cloud services becomes much more synchronized. I deploy new code, I also want to change the resource that I use. And it's led to all sorts of interesting things, because now you have sort of the classic disconnect. It's like a database schema change and an application change, right? How do I get this to roll out at the same time? Do I have two versions of the database? Do I make the code tolerant of having the old version, new version, right? Because this doesn't deploy, it's not a transactional deploy, right? It's like the one is a resource change, the other one is a code change, right? They might be out of whack. And the other thing that you observe even more telling is that traditionally cloud automation was considered the domain of infrastructure people, right? Here's your Kubernetes cluster, EKS or AKS, whichever one you have it, right? So infrastructure will make a script that deals with resources. And they like it that way because cloud resources cost money. So you have a separate team. It's like, you need a database? Fine, here's a database. Do with this database whatever you like, but you're not changing the resource, because I like to have the encryption on. I don't want you to put it in different availability zones, right? Basically, I control the resource as infrastructure, and application team is sort of using the resource, right? Putting database schema in, putting data in, pushing new containers on the Kubernetes cluster, right? So there's a completely disconnected rate of change. And that's why in a lot of organizations, cloud automation is considered kind of an infrastructure thing. Right? It's like, hey, I do this infrastructure thing, you do your application thing. And when I worked on EventBridge, right, this hit us pretty much in the face, that we said, this is not infrastructure, it's not integration, it's not separated from the application, it's really part of this application. So we also need to rethink how developers deal with it, right? So now developers need to write, CDK or Pulumi or CloudFormation, Terraform, whatever you use, right? So that needs to be in the hand of the developers, because the rate of change, the dependency now is in the hands of the same team. So distributed systems versus integration makes a big difference in terms of how your teams work together and the tools they kind of use and who owns the respective parts. If you want to drill on this a tiny bit more, right? So I said sometimes people blame Bobby and me for having created the ESBs, right? The enterprise service buses, who get a bad reputation. Where does that bad reputation come from? It's very easy to see on this chart. The ESB people had the old style integration view, separate team, lower cadence, right? Their ESB team was separate, saying, hey, if you need something from integration from the service bus, right, tell us and we'll do it. Ultimately, right, temporarily decoupled, right? So ultimately we will do it, but because the ESBs were programmable, right, they were meant to be integration tools for developers. Developers started to see them as part of the application, saying, hey, I'm doing this thing, I'm also going to change the message routing because my method changed, I have a different field, I put this thing, I update this. They see it all as once, and that's exactly where all this friction came from, right? The disconnect between, is this running like a distributed system, right, high level of control, same timeline, during development continuous, or is this integration? And that's what I said, the teams were set up for integration, but the mode in which the ESB wanted to work was a distributed system, and that's where all the friction happened, right? They would never get happy with each other because the two things would not align. So we can read actually a lot out of this. So what we learn, right, is, and probably belabor this a tiny little bit here, is what we learn is these solutions, right, they're socio-technical systems. They're not only characterized by their technical properties, but also by who has the ownership, who has the control, when are these things performed, is it the same team, is it a different team, do I need to coordinate, do I need to file a ticket, heaven forbid, right? All these things also really matter. I know this is an old article I wrote, right? Sometimes you have this architect's dream, like everything should communicate via XML. It's all loosely coupled. I'm very happy as an architect, right? And the development team pays the price because the thing has horrible performance. I need to marshal, unmarshal. I can't pass references. Like, I don't know what's going on, right? So you created a nightmare for the developers. So yeah, so here's, there's a nice hobby we have as speakers and as authors, and that is there's a certain status attached to having your own law, right? There's a Conway's law we cite a lot, right? Now, luckily, there's no law about making laws, so we can make our own laws. So this is Gregor's law of coupling, that when you think about coupling, one of the biggest determinants is how much control you have over the endpoints. If you have control, if you can make changes easily, you probably get away with much more coupling, and you benefit by having more efficiency, better tooling support perhaps. But if you have less control, as you do in a traditional integration sort of environment, you cannot afford that tight coupling. It pushes you towards looser coupling. So if I had to distill it down to sort of a single heuristic, this is probably the closest that I would have. Taking short breathers. So here comes a very short section. And that is, what is loose coupling is nice, but what is lousy coupling? And this is actually, I borrowed this sentence from a former coworker of mine from AWS, where we gave presentations at re:Invent and many other places, where he said, loose coupling is nicer than lousy coupling. Where do you find lousy coupling? Lousy coupling is coupling that you didn't see, you didn't know it existed. And the examples here are still a little bit abstract for two reasons, because A, I didn't get quite finish it, and B, they're largely out of AWS examples, so I didn't want to be too pointed, because this happens all over the place. I just happen to know these challenges with AWS better than other things because I used to work there. So let's go back to this topology decoupling, right? A talks to B, that is nice, but now I want to temporarily decouple A and B. So I put a queue in, right? Amazon speak SQS, simple queuing service, one of the oldest Amazon services, right? It all started with S3, EC2, and SQS. So this has been around for a long time. Very nice. Now, will this necessitate changes? And you could say, depends sort of how A and B talk to each other. If this was a Lambda invocation, maybe I do. If it was a Lambda destination, A wouldn't have to change, because the infrastructure actually sends the message at the end of the Lambda function, and you could change that from a direct invocation to a queue. So there would be ways that you can do this without having to change A, and that is cool, right? That's what the cloud does for you. That is serverless in action. But the key thing is that happens is the messages that you get are more likely not exactly the same. And sometimes for good reasons, right? Like a lot of messages have a source attribute, right? Because sometimes you are interested where things come from, but now they don't come from A, they come from other resource, which is called SQS. And also, this is largely historical, and again, I know these examples best from AWS world is, there's different encoding. Some messages have the message fields right at the root, other ones have them under a detail field. SQS, for example, does that. And the field is base 64 encoded. It's a string, which may contain JSON, but it's not like JSON fields that you pass directly. You need to decode it and then JSONify it from a string. So a lot of little nuances change. The header fields that are available. As I said, the name of the field that wraps everything. So this is often the stuff where people say, I made a cloud-based serverless event-driven architecture, so I must be the uncrowned king of loose coupling, right? Because I used all the buzzwords, modern technology, event-driven, right? And then a simple topology change drags that down immediately. You put a queue in the middle, some of the most simplest things that you might want to do, very basic topology change, and kaboom, right? More likely than not, B will no longer be able to read those kind of messages. So that is what we call lousy coupling, or we should better say like hidden coupling, where you think you made something that is loosely coupled, and perhaps you even paid the price for making it loosely coupled, right? It is asynchronous, it is event-driven, it's a little bit harder to deal with, to reason about, it has a little bit more latency, right? You took all these things into account, because as a payoff you get is this loose coupling. And then when you try to exercise the loose coupling that you feel you purchased, right? You bought it with the price of complexity, with the price of tooling, less tooling, with the price of latency, right? You paid all this price, and when you try to redeem it, something comes out and nips you in the rear. right? Because something that you didn't think about, because some services don't have the same data format, have different encodings, different field names, different structures. They wrap or don't wrap. Then you have settings about raw messages you can do. Is like this little weirdo stuff, and that hits you in the rear. So that is the lousy coupling, and that is something you need to be very careful about, because as architect you might brag, look at mine, as I said, my nice event-driven asynchronous serverless, right? The architect's dream, but in reality it doesn't hold, right? And that is lousy coupling. So you gotta understand the runtime you're sitting on, and so the inherent coupling that runtime brings with it, because it might undo some of the coupling that you worked so hard to get rid of. So queues, I said queues is sort of the simplest thing you can do. If you pay close attention, right, I said at the very beginning, the simple stuff is always deceivingly simple, and the same thing is true with queues. Yeah, queues are actually much more magical than it might seem. There's a lot to be said about queues. I like queues a lot, obviously, right? It's sort of the heart of asynchronous messaging, right? I can put stuff in a queue, and the other side can take it out whenever they please, right? It does all these cool things, but there is a truth here. That the queues invert control flow, but they also require flow control. So, and that's not a play of words. There's actually real architect insight behind this, so let's parse this out. So I said earlier, right, this talk in a way was 20 years in the making. It took me a while to get here. And the real insight was that enterprise integration patterns with the 700 pages is really only telling half the story. It's telling largely the story of data flow. It talks about how, what message goes where. Like, what does the message look like? Does the message format change? Does the message get split into different pieces? Where does the message go? Routing, right? We saw this all at the beginning. So it talks very much about the message as a piece of data and how that message sort of runs through your system. Pretty cool. All the icons, all that stuff, the patterns, right? Fantastic. What it doesn't talk about is how it actually gets there. Like, who runs the active threads? What is pushing? What is pulling? Like, what happens with those retries where we sort of pretended we don't need to deal with them, right? What if it retries 1,000,000 times and it still doesn't go because it's a poison message, right? It doesn't talk about those things too much. So there's a other half of building good distributed and integrated systems, and that is all about the control flow. It's like, how does the message actually get there? What happens one level underneath? And you need to have both, right? You need to design the system so you understand the overall structure and the data flow, and then in order to deal with the operational characteristics, like how does this thing really scale, for example, how resilient is it? Well, you need to really look at the control flow. You need to understand how the message actually gets there. It's not like magic. So took a while for us to realize this, but enterprise integration patterns is 90% about data flow and not about control flow, so we will fix that. Go on, bing. There we go. So I said at the very beginning when we had the slide about, we said it's never just two boxes and a line. We said, oh, is this data flow or control flow? And you might be, are we splitting hairs here? No, we're not splitting hairs, because they might point opposite directions. So messaging is relatively easy, right? The message goes, like A sends the message, and the message goes from left to right, right? So data flow and control flow are aligned. If this is a remote procedure call, if something goes in both directions, right, it gets more interesting, because the sender is doing something and the receiver is doing something, because it's either returning data or maybe actively sending data back, right, if these are two separate message channels. And you can quickly flip this around, right? If something polls, the right-hand side initiates the conversation. So the right-hand side owns the control flow, like how it gets there, right? The right-hand side is active. It controls the rate of polling, when it polls, right? So the right-hand side has control, so in the little world of the sense of the word, but the data flows from left to right. So they're completely inverted, 180 degrees, right? The right-hand side has the control, so the right-hand side controls the left-hand side. If the right-hand side polls a million times a second, right, it takes the left-hand side down, like it has control over the system, but the data that flows from left to right. So data and control flow can point opposite directions. So I always tell people, when you draw these arrows, be careful to tell people what you're denoting, because you might be drawing the arrow the wrong direction depending on what it's supposed to indicate. So, both are important, and they're separate, and they can point opposite directions. Now, the nice thing that the queue does is it inverts this control flow, right? Both of them are active. Both are active elements. One element actively writes in the queue. The queue generally doesn't poll anything, right? You write into the queue because you have control, and then you also actively fetch from the queue. There's always little, especially in the cloud, some things support both push models and pull models. We come to this a tiny bit, but by and large, when people think about the queue, you poll from the queue. SQS, right? You fetch. You go and fetch from this queue. Generally with Google pops up, right? You go and fetch from this thing. So the control flow is inverted, right? On the left one points this way, and the right one points this way, right? And that's how the queues can do these magical things, right? That's how B, right, the right-hand side, can poll at 10 messages a second, right? It has a classic polling rate, and the left side can be the Wild West, right? Stuff is arriving at all sorts of weird arrival rates, and the queue basically makes all that noise go away, and the right-hand side gets a nice, sane, steady flow of messages, right? That is the magic of the queue. We don't even think about it so much, but I would say give the queue a little bit more appreciation. This inversion of control flow is actually magical, right? That's a very important part of building distributed systems, right? So why do we look at control flow? Well, control flow defines many of these operational characteristics, right? The whole thing that if B isn't available, A can still put messages in, that comes in because B is actively polling, and when B is not polling, nothing happens, right? It's not a single control flow that goes through. The two are opposed, right? They run independently, so B can go faster, can slower, A can go faster, slower, right? This is what gives the systems the resilience and the scalability, and especially how this happens, well, outages and high load. Right? Those are the two scenarios where your system behavior comes very interesting. Brownouts, blackouts, right? So one component isn't functioning, or the other one is, right, you have high load on your system. How does your system behave? A lot of that hinges on control flow, whether it's synchronous, asynchronous, left to right, or right to left. Now, many cloud services make you choose. So anybody dabbled with AWS, there's EventBridge and there's EventBridge pipes. EventBridge is a push model, like a S3, like a change in an S3 bucket will publish an event, and that event is driven, is pushed, right? That can go to EventBridge, and you can filter and route it. If you have a DynamoDB stream on SQS as a source, that doesn't push anything. You need to pull. So you need a different service. You need to use EventBridge pipes. Coming back to maybe lousy coupling is a little bit harsh, right? But let's say you had something push-oriented and you put a queue in. Now you need to pull. You need a different integration services, right? You cannot attach EventBridge to a queue. All right, you can only attach EventBridge pipes because one can push, one can pull. Different cloud providers have this slightly differently. Like in Azure, you more likely can choose. In AWS, right, the pushing versus pulling comes with the service. Finally, I checked the documentation rarely ever says the words push or pull or control flow, right? It's just like you're supposed to know this and figure this out on your own, right? And inverting the control flow is nice, but it also increases latency, right? Polling is kind of inefficient at the end of the day in two ways, right? Looking for something that isn't there is inherently inefficient because you're doing work for nothing. But also, if you want high throughput, right, the polling time waiting on the next polling, basically no data gets processed, right? So you have a cost there. So you should consider this kind of control flow. So this hasn't taken us 20 years. This only take us about 6-7 years where we said, hey, can't we just extend the Gregor notation with control flow? And the answer is very easy. And funnily, this wasn't even Bobby's and my idea. So a friend of mine, Ivan Gewurz, who came up with this, and we just made it look a little bit prettier and gave it all names. Where we said, hey, you can extend this visual notation. If something pushes, like the sender, right? A sender is something active. You send a letter. The letter doesn't pull itself sort of out of your drawer, out of your hand, right? Like you post it, right? It is active. You have control. You decide how often you do this. But a source is passive, right? I fetch something from a source. A DynamoDB stream is a source that I fetch from, so it has that little nook. And likewise, a sink is just sitting there waiting for stuff to be poured into, right? The sink is passive in this way, right? Versus a fetcher, right? That is the thing that fetches. And now, if you have these kind of noses and nooks, you can realize, oh, well, if I have a source, I need a fetcher. DynamoDB stream is a source. EventBridge pipes is a fetcher, so they will fit. Versus, EventBridge will be more like top right is like a sink. Like you cannot have two noses or two nooks with each other. So suddenly this becomes very intuitive, right? It's expressive, and this is the power of these visual diagrams and these styles, where now I can have the data flow and the control flow with it. Little bit out of scope for this short deep dive is batching, right? I also thought about I can extend this, whether does the fetcher really only read one message at a time, or does it read batches, right? You can play with this because batches have their own thing, right? They're more efficient. If you fetch and you get 10 messages back, right? It's more efficient than polling 10 times. But what if one of those 10 fails processing? Right, can I return one? So all the cloud services deal with this, right? So you can play with this notation as well. I made like double noses for things that fetch batches, for example. So we are, I joked about, computer scientists always thinking everything is binary. In this case, it works to our favor. We have two sides. Each of them have two combinations, right? Nose out, nose in. So 2 to the second is 4. So that's where the binary system helps us. It's 1, 0, 0. So there's 4 things we can build. And they have names, right? Something that pulls through. Control flow from right to left is a puller, right? It actively pulls, but then it needs something else to pull it. The pusher, similarly, right? It pushes it down, so it goes to another pusher or maybe to a sink. A driver is something that's active, right? So, for example, if you need to connect a source and a sink, you need a driver, right? Because something needs to actually get the machine running. And then, unsurprisingly, the queue, because it inverts control flow, is the thing with the 2 nooks. It doesn't do anything on its own unless somebody pushes data in or somebody pulls data out. I know, even if you didn't know much about this, right? If the cloud services had this kind of notation, it would become fairly easy to put something together, right? DynamoDB, has a nook, so I need the pipes thing which has the nose, right? And only that can fit on it. It's another dimension of building the system, and actually expanding the icons to this, right? Makes you think and talk about whole new aspects of this. And that is quite powerful. It's the same as with the Gregor grams, right? The little icons, they look very simple, but the power of the integration patterns was that people people think more broadly about the solutions they build, and they can also talk more efficiently and more precisely about it. It's like, hey, I think we need an aggregator. Oh, an aggregator is a stateful component, right? I need a completeness condition to know when it's done, right? People talk about this stuff like it's very normal, so it really enriches their design space, and this does the same thing, except on the control flow side of things. So this is actually, we thought it's more than cute little noses on the icons. This is actually a relatively big deal. Right now, all the cloud services do this, right? They all have push and pull models, and I said some of them have different kind of subscriptions. So GCP pops up. You can choose a push or pull subscription, like call me when you have something, or let me fetch it. So you choose this in the same service. Azure, I have to admit, I don't do as many things with Azure. Something I should fix, right? It also has pull and push delivery, and it has some cool things. If you choose push delivery, the question, of course, is always at which rate does it push, right? So it does pretty cool things, like Azure has auto calibration based on how your downstream reports errors or not. It ups the push rate and it sort of recalibrates. Pretty cool stuff in there, right? But with the icons, this all becomes very obvious. And then interestingly, like in Amazon land, it is more tied to the service. You generally don't get to choose, right? Unsurprisingly, the queue is exactly the way we said. SQS, SNS is a pusher, right? Quite interesting. So those are different, even though they are a publish subscribe channel in EIP language, and in competing consumers, a point-to-point channel. They actually have opposite noses on the right. And then I said event bridge versus pipes, right? The one is a driver and the other one is a pusher, if we use the vocabulary from the previous slide. And immediately it makes sense about what fits together with what. And also you can see slightly different philosophies, right? It's like maybe those two guys like to have fewer services, but the services have different interaction models, versus from an operational perspective, maybe AWS decided that it's more efficient to implement if one service does one thing, whichever it is, right? People often say these services, the clouds, are too similar to each other. They're all the same. They're totally not the same. Once you look at the operational characteristics of this stuff, the clouds are actually fairly different, right? And this is a great example of that. So what you find is when you see a pusher in a cloud, it is rarely a straight-through pusher. Like straight-through pusher is, right, would mean 100 messages per second go in, 100 messages per second come out, right? When you look at the picture, so the left side could be, let's say, event bridge, right? So event bridge, it does filtering, right? It does transformation. So classic event routing. Event comes in, where should it go? Do I filter out some fields? Maybe it goes different places based on different fields. I do some transformation, right? Like classic event router. And in the big picture, I hope you can see this, the blue box basically looks like a pusher, right? It's like you push something in and it pushes back out, right? So that is what SNS does. This is what event bridge does. But internally, actually, they have worker pools because they need to scale out somehow. Remember, these are shared cloud services. This is a multi-tenant environment. You're not the only one who puts messages into SNS, right? You get your own instance, right? You get your own SNS, your own SQS, you get your own event bridge, but it is ultimately a multi-tenant system. It's not like Amazon gets like another server out and provisions something on that for you because you have another event bridge bus, right? These are logical resources that share infrastructure. So the way this infrastructure scales is by scaling out. And it scales pretty handsomely. This is, usually in the hundreds of thousands and millions of transactions per second, right? Like globally, it has a massive scale, and that works only because it has a queue inside and it has worker pools that scale up and scale down. So it looks from the outside like a push delivery service, but if you look on the inside, right, it actually has drivers. This is one of the reasons when you look at a lot of these cloud services that they have out-of-order delivery. And we'll look at this in more detail later, right? Because messages can take different paths, right, if it's scaled out, so they can get out of order. It also means that this can do traffic control. It can do rate limiting, right? You don't always, if you put like 10,000 messages per second in, you don't necessarily want 10,000 messages a second coming out, even though the icon looks like that. So yeah, there was we often joked about there is actually a queue in Event Bridge in AWS and many of the other cloud services, right? On Azure, same thing, because it has push and pull delivery. It must have a queue inside because otherwise it can't do pull delivery. And even on push delivery, it self-calibrates the rate, and that can only be done because it has a queue and a driver. Something determines the delivery date, and it tries to sort of self-calibrate where that is based on the error rate that it gets from the downstream consumers. I mean, forgot the detail. Is like if the error rate is above a certain percentage, right, that it gets from the downstream consumer, it starts backing off. I know that he can only do because that driver, right, dynamic rate, it sits right there. That driver has a dynamic rate that self-calibrates, and if it has a driver, it must have a queue, right, because easy as that, right? If the source pushes data in and it has a separate driver, it must have a queue. There's no other way to put a distributed system like this together. So suddenly, right, you can reason and talk about this stuff in a reasonable amount more detail, and that is the fun of these pattern languages, and particularly the visual pattern language, that Now you have a whole different level of conversation, how the system behaves. Now it doesn't shockingly surprise you that the latency of the service is maybe a little bit higher than you would have thought. It's like, hey, what is this thing actually doing for 50 milliseconds or 100 milliseconds, right? It's like, I'm not asking it to do that much. It's not parsing your messages and routing it. That doesn't take 50 milliseconds. It's largely sitting in a queue and waiting for a worker to be available, right? It quickly answers those questions, and you know how things get out of order, right? Customers always come like, oh, I want in-order delivery, and we come to this later, and it's like, well, that is a trade-off. Yes, it's nice to have in-order delivery, but it comes with a whole slew of other problems, including that you cannot have parallel processing, right? And try to do this single-threaded at 100,000 messages per second, right? Maybe won't work that well. So having this notation and having these patterns now gives us a lot more understanding. So the one thing is, and some of the guys, I read this book way back when I was in school, then Norman actually came to our class. This is called an affordance. So if I don't know much about these cloud services, but if they have little noses or nooks, I intuitively know that, I can only put the nose on the nook, right? If DynamoDB Stream has a nook, and I go through all things that match, right? SQS doesn't match, SNS doesn't match, EventBridge doesn't match, pipes matches, right? Even if I don't know anything else, I intuitively do the right thing, And that's what Dan Norman calls an affordance, something that looks the way so that you naturally do the right thing. This is a negative example. Right? It's like you put a handle, what do you want to do? Like your hand is already, the fingers are already like this, right? When you see the handle and what do you want to do? You want to pull. So that's why fire exits and fire doors don't have handles by law. They either have push plates, right, that you cannot even pull, or they have these push bars, right? And now they're smart enough that the push bars are not in the center, but they're off center, so you know where the hinge is, because when there's a fire, you don't look at the door and analyze sort of what do I need to do, right? But instinctively the doors are made so that there's an affordance, so like you naturally do the right thing and you push on the left side if the hinge is on the right side, right? Honestly, stuff like this happens. Like people die in fires because they push on the door on the wrong side because they panic, and then everybody piles up, right? And weird stuff happens. So affordances are very, very useful. Make things the way that the right way of using it is natural, and that's what the noses and the nooks can do. Luckily, here's no fires and people don't have to escape, but it's stuff like you cannot put the wrong ARN on the wrong service, right, for something that doesn't match, because you will quickly see that that doesn't work this way. So here's like, what fits? So I have a source and a sink. Even if I don't know anything else, right? If I paid attention in sort of, when I was 4 years old, like when I was playing with a little telephone, I had my little puzzle games, right? Like what shape fits what? Right? I would be able to solve this kind of puzzle, right? I need a driver and I need a queue. So these little things help us actually quite a lot, because in the heat of the battle, right, I might make silly mistakes, and this keeps me from making these silly mistakes. So what we learn is, so message queues invert control flow, right? So that one we covered, right? Because the little noses, but they require flow control. So I need to talk about the second half of this thing. So comes to our next truth, and this is exactly about flow control. So this is the answer to flow control, and that is pushing things to somebody else at the arrival rate is not called integration. It is commonly called denial of service attack, right? You might get things at 1,000 messages a second, but the downstream API might not like this at all. And that's what I said. That's why all these cloud services have auto calibration, rate limiting, EventBridge pipes. If it calls an API, it has an explicit rate limiter. It has a setting how many messages per second you want to send, right? It has this kind of flow control. So what you don't want to do is just like keep piping things down the pipe, right? Hoping that the downstream will handle with it. That will not work. So what you can do is, or especially under high load, if you don't consider flow control or load shedding, right, those things, we'll come to this, right? If load gets excessively high, what happens is that your system gets busy accepting new requests, because there's no flow control, right? So it's like it just keeps piping things, basically shoving things down your throat. So basically your system is busy accepting new requests, and it has no longer any capacity to actually process those requests. Common terms we use is throughput versus goodput, right? Like a request that you get that comes back with a 500 error or an overload error, let's assume this is HTTP, right? That is not useful throughput. It's like, yes, you can say, oh, I handled this request, but you didn't really handle it. So technically you did, but from an application perspective, you didn't, because you returned an error because your service was unavailable. So maybe you took the HTTP request, but you want to actually go and do something, but the other system is already overloaded, right? You can't actually do anything, so return an error. So most of the systems which are synchronous and don't have a decoupled control flow, they don't have flow control in them, they tend to have this red kind of behavior where throughput goes up to a certain point, and then they saturate, and then throughput actually drops again, because there's no more capacity to actually process all the requests that is accepting, and that's where queue-based systems tend to do much, much better. Some folks might remember terms like staged event-driven architectures, different stages with queues, right? This very much comes out of this idea. Systems that behave well on the high levels of load because they don't have this nasty kind of pushing it over the edge, pushing it over the peak, and that's what queues are very good at doing for us. And the way to visualize this, right, the pictures admittedly I showed so far, they depict a dynamic system, right? It's loosely coupled, it's asynchronous, so it's dynamic in a way, but we didn't really have a strong dynamic picture. We always showed the structure of a dynamic system, right? So now we should look actually at the behavior of a dynamic system, like, well, how does this actually sort of take place, right? And that's when you do this with queues, right? You find this is what a queue does. If the arrival rate varies widely, right, the consumption rate, again, I drew the control flow here, notice the arrows, right? It's not data flow, it's control flow, right? Because the control flow is different, I can limit the consumption rate. That's the magic of queues, and that is much easier to tune a system. And if I have a massive overload, right, I will not drop down because I keep processing at the maximum rate that I can, so the throughput remains stable even though the arrival rate goes up. Now, of course, there is a question here, like what happens if nothing comes in? Well, that's easily answered, right? If nothing comes in, the queue goes empty and nothing comes out. But the second question is, of course, the opposite. What if this keeps going? What if I have a 5 messages per second API downstream, but I have like 1,000 messages per second arriving, right? Is this gonna continue forever? And the short answer is no. Nothing is ever unlimited, right? It's like ultimately the queue fills up, or two things happen. A, the queue fills up and I have operational issues, or the processing time is so slow that actually processing the message is no longer valuable. If this is an update, the stock price or something, and it comes like a month later, it's like, I now did useless work, right? I did work that no longer had any value. So there is 3 main mechanisms of flow control that we can use. And the first one is built in almost any commercial queue. It's time to live. It's message visibility timeout. It has kind of different names. It's like basically, how long do I want to hold a message in this queue until it's no longer valuable to actually process it? And people always struggle with this a little bit because they say, oh, all my messages are valuable, right? Because this could be a bank transfer, this could be important data, right? But the key of the matter is, if you don't do any of this, the system will pick its own flow control for you, right? If you don't consciously shed anything out of the queue, nothing else can be added to the queue. So like the default you're getting is tail drop. Right? So you need to decide. Like if you don't decide, the system decides for you, right? If you never shed anything old, nothing new can come in. That might be what you want, but it might also be not what you want, right? So tail drop is the opposite, right? It's a classic sort of 503 overload, like try later, right? Kind of thing. You don't accept new requests because you know that the new people come in will wait so long that ultimately time to live would trigger, right? And you know wiser. So it makes no sense to let the messages be in the queue for like 10 minutes just to know they're going to drop time to live. Like you just say, basically, people, you know what? I know it's going to take longer than you want, so I'm not even taking anything. Right? And hopefully I'm returning an error is in terms of just instead of just going to def null. Now, the nice one, the elegant one is back pressure, that if you tell the systems before you, the upstream systems, like, hey, people, can you just ease off a tiny bit? So they might change the UI, they might do other things, they might rate limit themselves, right? Back pressure is actually a very nice and elegant way. Now, funnily, almost no cloud service or queue implements that natively for a simple reason. Time to live is within the scope of the queue. You can look at the age of the messages, right, and shed the ones that are old. Tail drop is relatively easily. You just like, okay, you shut the API down. Nobody is putting anything into my queue, right? Back pressure requires you to know the source, right? You need to go back to where things came from. You need to make a signal somehow upstream, and that generally has to be hand coded. Yeah, it's also a form of coupling, clearly, right? If you tell the upstream system that, hey, I'm a little busy, can you ease off a little bit? That means you know who your upstream system is. If that ever changes, you have a change, right? Those are the trade-offs we talk about. But basically, you need to do one of these things to make a reliable system. As I said, if you don't do anything, it sort of automatically picks something for you, and in most cases, it is probably the tail drop. Yeah, and a nice way to think about this, right? Why? So this is load shedding, right? There's stuff that wants to be done that you know you're not going to do. You're actively shedding load out of the system, right? And the nice thing is, like, either you avoid doing work that is no longer relevant or avoid starting work that you won't be able to complete, right? If you know the queue size is 15 minutes, and generally people don't wait longer than 10, there's no point in taking anything in because you'll shed it anyhow, and vice versa, old stuff that people no longer want, you're going to shed. At AWS events, we built this serverless presso where people could order drinks via a nice serverless application, and we very quickly ran into all these kind of problems because you have two baristas, classic rate-limited back-end, legacy, you can say, right? Legacy back-end, certain rate limit. We very quickly learned if people ordered a coffee and we knew it was going to take 10 minutes, nobody would be there to pick up the coffee, right? We would be doing worthless work, right? We did work that is no longer relevant. In this case, it was a waste of food, it was a waste of resources. So you can see this stuff in real life kind of situations. The only place where this kind of does seem to work is sort of the airport, because everybody really, really does want to go, so nobody leaves the line, so there is no load shedding, I guess, and that's why the lines get so ridiculously long, because nobody actually wants to give up. But in most other cases, one of these things has to give. So that's what I say, back pressure is generally somehow you need to tell the upstream system, hey, ease off a little bit, right? Either tell the user, or they need to have another queue or another way, or maybe they have a database or some way of holding stuff so that you don't do the things we just talked about, right? Accepting work that is no longer relevant, or accepting work that you know you will not be able to complete. So that most of the time you have to build yourself. Yeah, this is conversation coupling, right? The left side needs to know to check the flag, right? Should I still be doing stuff? Yes or no, right? This is a contract, a conversation you have. If that changes, right? Both sides change, right? That's a form of coupling, but I would say in this case, perhaps a good trade-off to make. And here is what I mentioned. This is serverless presso. It's like an open training from AWS, very popular. These people get free coffees. They get to learn a little bit about serverless. They also get to learn a little bit about queues and control flow and flow control. And there is this thing where, well, first they make sure the shop is actually open. Does this point? I think it's not strong enough for this giant screen. It goes to list executions. What does list executions do? In this case, it's not a queue. It's actually workflow driven. This is step functions. As you can kind of see, it's like a workflowy kind of thing. So it looks at the number of process instances that are active. It's kind of interesting how this works. In a way, it's kind of like a queue, right? You have these active process instances, and how many open instances you have is kind of equivalent replacement for how many things you have in a queue, because ultimately every process instance is going to go against a limited resource, right? Every coffee gets made by the 2 baristas. So in this case, the queue is kind of in a way represented by number of workflow instances, and right there the names are a little bit weird, right? Basically what it means, it has this choice state, and if the number of open executions is about a certain level, right, it actually passes and it puts an event that the order was not placed. So you can see this real life, and this is like there's like serverlesscoffee.com. This is a real workshop. So thing you see here, clearly back pressure, right? If the downstream system, in this case, it can tell how much load is on the system because it can easily query the number of open process instances, and then it backs off. It tells the user, hey, look, you're not going to want to wait this long for your coffee, so don't even bother ordering it. I think I gained some weight. The clicker no longer goes through my body. I need to turn before I can click. Now, talking about flow control, I think I flowed you guys pretty well. It's probably time for a short break. I need to remember, what time do we finish? 4:30, right? Okay, so it's 3:08. Is it fair to have a break till 3:30, 22 minutes? Yeah, nobody will disagree, right? And I'll watch you going out and coming back in, and I'll have more ideas about flow control when you come back. So good luck getting through the rate limited queue on the way here. See you in 21 minutes. I already took one from you. So audience. So thank you for coming back. We have a few more, and I'll see how we do for time. We should be, because I said some of this is still a bit fresh, and not all the slides are sort of as pretty as they could be. In return, I have more than 10 points, so it pays off to stay till the end. So we are at number 7. Synchronous. Yeah, we started this all by being asynchronous. So now we talk about synchronous. Synchronicity, I think, is the word. And we talk about resilience. So resilient is a nice word. Here this. Yeah, I have this kind of thing where, like, if you're synchronous and 2 things happen at the same time, right? Maybe that leads to odd things. But more importantly, let's talk about the word resilient first, and how you make a system. Why do you want the system to be resilient? You want the system that sort of can deal with failure, right? Like something goes wrong, but a resilient system stays operational. But it helps to be a bit more precise with those kind of words, right? So the easiest way to keep a system available is to make the system robust. Robust is actually good, because robust things are things that don't break, right? That's why they're sturdy, they're robust, they don't break easily, and that is very nice. It's like this castle, right? You have thick walls, somebody comes, throws some stones at your walls, nothing happens. You can lead a very happy life in your castle until, and we all know how the story continues, until somebody comes with a very big stone. Right? So the problem with robust systems is, they're designed not to fail, but they leave open a little bit the question of, now what happens when it actually fails? And that's when we make the decision from the transition from robustness to resilience, because resilient systems think very clearly about what happens when something does go wrong. So rather than avoiding disturbance, avoiding failure, the resilient systems deal with failure. They can recover from failure, right? And the common thing is, rather than just having thick walls, I have failovers, I have standbys, I have sort of other instances, I'm distributed, right? That makes me resilient against failure. So it's not just about the MTBF, right? So robust is trying to maximize the MBTF, the mean time between failures, and the resilience is looking to minimize the MTTR, the time to recovery, ideally 0, right? Something goes wrong, but you actually never see it. Now that's good, right? But now you can do something even more clever, and that is, how do I know my system is actually resilient? Do I need to wait for something to go wrong, or do I actually test it. And if I test it, in which environment do I test it? Do I test it in a testing environment so I know my testing environment is resilient? But do I also know that my production environment is resilient? So the idea comes that, hey, maybe it's not such a weird idea to inject some disturbance into my environment, right? I'm basically doing what most people consider the worst idea. I intentionally break stuff, right? And like chaos engineering, chaos monkey comes out of this, right? The left-hand side is very much, I really don't want to have anything go wrong. And the right-hand side, the anti-fragility, is really about if I intentionally make things go wrong, I actually get a more resilient system. So putting disturbance in the system is good versus on the left side, it's considered bad. All right, and that always reminds us these approaches are sometimes causing us to do the exact opposite of one another. Now, what I always tell people is, don't throw the chaos monkey in a system that is not resilient, right? You need to be, a robust system will not like the chaos monkey because once it falls over, it falls over. So you need to do these in proper sequence. You need to become resilient, and then you can become more resilient. So anti-fragile, right? Anti-fragile means something becomes stronger with disturbance. The more you sort of chisel away at it, the stronger it actually becomes. Many of you guys may know I like to use real-life metaphors for things. I always say, when people, if you need to explain chaos engineering to someone, right? And people come like, why would you intentionally break stuff and do this in a production environment, right? Isn't this a really dumb idea? That one analogy you can use is one of the very resilient systems we have on this planet is the human body, right? We're pretty resilient. Now, what is a vaccination, right? We just gladly got through all the pandemic stuff, right? But vaccination is injecting a small amount of disturbance into a system to make that system more resilient, right? So we do it all the time. So it's actually not such a foreign idea to inject disturbance into these complex systems to actually make them more resilient. The other way to characterize this, and you need to be a little bit careful with the wording, is if you have a system where you intentionally inject failure, you have a system that is always failing, right? Because you're always putting some failure in. So the amazing characteristic of such a system is that if something really fails, the state of the system hasn't changed, right? Because there's always some failure in there. So if it's a little bit more failure, right, it's like basically nothing changed. Now, the reason I said be careful with how you communicate this is it might be hard to go to your CIO and ask for funding and say, hey, we're going to build a system that's always failing, right? That might be a harder sell. So you need to explain a little bit. But the magic is really, if you have a system that you always inject disturbance in, if a failure happens, the state of the system doesn't change, and basically you don't need to be freaked out about it, right? So you inject failure to improve. So that gives us a little bit of thinking, right? If you want systems that survive in the face of disturbance, in the face of failure, we need to think about, are we relying on the robustness? Do we have something that's resilient? Or are we even one step further where we're constantly validating and improving the resilience by intentionally injecting failures? Well, do I have a funny clicky button? Yeah, so the term anti-fragile is borrowed from a book from Nassim Taleb, right? The guy who wrote The Black Swan and anti-fragile, right? We always says anti-fragile is not, sort of it's not like sort of the opposite of robust. It's not something, that's easy to break. It's something that becomes stronger with disturbance. It's like a rumor, right? The more you try to quell a rumor, the stronger it actually becomes. And because that guy is also smarter than me, he has all these kind of analogies, like Phoenix always rises back from the ashes versus Hydra has the 7 heads. So if you like this kind of stuff, perhaps have a look at the book. It's kind of an interesting way to think about the world in a very different way. But we come back to messaging systems. The key thing that we realized for us, remember we talked about integration versus distributed systems, and the difference wasn't in the technical part, but it was in sort of the scope of teams and timelines, and who does it when. Very similar with resilient and anti-fragile systems. Like robustness is largely an infrastructure, right? We buy good servers, right? Or we have Oracle rack or something. We have some high availability infrastructure. And in a way that's convenient, right? Because one team deals with it. But in a break, we just had a short discussion about operations and applications teams, right? How they work together in this kind of world. If you think about it, if the infrastructure team is the one who is in charge of keeping the system available, you're basically asking one team to make up for all the mistakes that another team made, right? If the application team built something that falls over easily, right, the problem originates over here, you're asking somebody else to basically go fix the problem somewhere else. And, if you put 2 and 2 together, fixing problems that occur over here, over there, isn't such a clever thing. It's like the drunk guy who's looking for the keys over here, and people say, what are you looking for? And the person says, oh, I'm looking for my keys. And they say, well, where did you lose them? And the person says, oh, over there, right? And it's like, well, why are you not looking over there? And they say, oh, because that's where the light is, right? It's the old stupid joke, right? People look where the light is, not where the problem actually originated. Only reason it's marginally funny is because we do this in real life all the time. So if you want something to be resilient, generally the application needs to help a little bit, right? This can be of, retry logic, having primary and secondaries, right? You can wrap some of this into common libraries, but basically you can no longer say, I don't care, right? Infrastructure, please, solve all my problems. It is everybody's on the hook. And then the anti-fragile system, that really requires the human part, the processes, the kind of mindset. It's a different way of thinking, a different way of working. So it requires a different scope of operation. And that's why these things are often so difficult to do. It's not because it's magical, technical stuff that nobody can understand. No, we're pretty clever people, right? We figure this out. The reason these things are difficult to do because the scope of the solution expands. It's much harder to sort of teach people the value of chaos engineering, build these kind of feedback loops, get development and operation teams to work more closely with one another, right? Those things are much harder to do, and that's why building these systems often becomes a challenge. So one way I try to depict this transition from just being robust to being resilient, right? Robust is basically you have sort of a disturbance and it puts your system, this is like the state of the system. This is a little bit sort of complex systems thinking kind of notation, right? You have the state of the system, you have some disturbance, and ultimately it moves the system from an operational state into a failed state, and what you try to do is make that the least likely as possible. Versus the resilient system has a correcting action that gets the system back into an operational state. The anti-fragile systems, they generally require a secondary loop. And you can see this in reality a lot. So in the cloud, a lot of people use autoscalers, right? And they have sort of this right loop, right? So more load comes, they scale up, less load comes, they scale down. But the question is, how well does this autoscaler actually work? How quickly should this scale up? What should the limit be? I've heard, I once was an event, I heard this really, really funny story where somebody had built, we talked about load shedding. So somebody had built a load shedding logic. So when the server was highly utilized, it would replace some components with simpler components. Like it would have a fairly complex algorithm. These were like recommendations or routing or something. They would do a fairly expensive calculation, and when load was high, they would replace that with a very simple calculation. So what they also had an autoscaler. So what they did is the system ran at high load, so the application decided to reduce the load by swapping out basically the module that it was using, then the autoscaler realized, oh, the server isn't actually that much utilized, and it would scale down the number of available infrastructure, and this thing played sort of one off the other, then like, oh, the remaining infrastructure, the load was high, those nodes would also switch, right? And ultimately the thing scaled itself down to zero. So you can have funny stuff like this. So the more you automate the right-hand side, the more you as a human team need to actively deal with it. Right? It's one of those things, if your system deals with the simple outages or the simple disturbances, by definition, you only get hit by the really nasty ones. Right? The good news is that happens less often. The bad news is, yeah, whenever you get paged, it is like a nightmare, because if it was a simple scaling or a simple temporary outage or circuit breaker, all that stuff we build into the system, so this all works. Now you only get the stuff that really gives you a headache. Now, if you need more arguments, right, about injecting disturbance into a system, what do the firemen do when they're not polishing their trucks, right? Because in the reality, the lucky truth is it doesn't burn that often. It's like, well, here you go. The firemen set fire. So they do the same thing. If you need something that is a critical piece, right, that needs to be highly resilient, yes, they do inject failure. Now, you could make the argument that they're doing this in the pre-production environment. Fair enough, right? But that is where we have an advantage, because we do it with software, so we don't actually set our servers on fire, so we can even do this in production. The airport might not be happy if the firemen did that. So, resilience. So that was a little bit the warm-up. Now comes the interesting part, which is like one way we get resilient is by retrying, right? Something went wrong, something failed, so I'm going to retry it. On one hand, it's a little bit funny because, I said earlier, as computer scientists, we always like to think the world is so binary and predictable. Like it's all coupled, loosely coupled, tightly coupled, right? We always like things to be very predictable and one thing. On the other hand, we always believe that trying the same thing another time leads to different results, right? Kind of funny. And worse yet, often it does work. Right? So you do exactly the same thing, and once it didn't work, and now it does. Right? It should make us wonder sort of how we build systems a little bit. But here comes the truth. Right? Retry logic makes small problems into big problems, and nothing has brought more systems down than retry logic. So let me explain to you what I mean. Actually, I'm going to do one thing. I'm trying to be clever and turn my, because I have a little bit of my range extender, put this on the other side. So yeah, so what happens is, right, there's a small problem, and the small problem turns into a big problem. Yeah, we didn't change the oil regularly, right? So we had a small problem, and ultimately the engine fails, and now we have a big problem. So the thing is, the sort of, I was going to say magic, but it's black magic. It's like bad magic. So the unexpected thing that retry does, right? It amplifies the load of the system, right? Like normally, if everything succeeds all the time, there's no retries. You get 3 requests, you process 3 requests, you're done, you go home, right? Life is very good. Now, if failures happen, remember, like you need to keep in mind, the failure itself is not a sort of zero resource computing action, right? Something happened, and somewhere along the line, you started processing, you try to start another thread, or you go to the database, you try to get a lock on the row, like you're doing some work, and then somewhere that work fails, right? And then, things go back to start. So you did some work, and now the retry comes. So you do the work again. So retry is actually amplifying loads. And there's like a very clever quote. Oh, the screen here is much bigger. This is from Mark Brooker, like very famous AWS colleague, super clever guy, right? And he made this really nice observation, right? There's like 2 ways to bring a system down, right? To get it overloaded. There's too many first tries and too many second tries, right? And the reason I'm saying, that retry has brought my system down than anything else, it is the second tries, right? And back pressure is about making less stuff coming in, right? And backing off is about limiting second try. So backing off is, making your customers, making the clients of the system who are inclined to retry, making them retry less frequently. They back off so they don't overload the system in this way. And this is common, like in networking, we do things all the time. There's nice papers about this. I think I put this from probably Mark's paper as well, where the one thing you do is if you have something failing, exponential backoff is a pretty well-known pattern, right? So if there's a little problem, you try again quickly, but if that second try also didn't succeed, you back off. You wait longer. Because A, you've been waiting already longer, so it's more acceptable. Like, if this is sort of a second later, it's more acceptable to wait another 2 or 3 seconds to retry versus the first retry. You want to be quick. So this has become very common. Most networks work this way. A lot of cloud services work this way. Actually, the cloud APIs have a lot of this built in as well. It turns out, though, that if there's a sudden spike where sort of very briefly the system got overloaded and everybody uses the same backoff mechanisms, the spike just repeats predictably. Like, the picture is beautiful, right? It's just like doubles every time, right? But it's the same spike. So like, boom, every time the system still takes a hit and cannot process all these requests. So what folks do is they introduce jitter, you introduce variance into the retry wait time. So you back off, so you wait longer intervals before you try again, and you sort of add a little bit random element into this so that not everybody retries at the same time, and that gives the system a much better shot. Right? When I said, retry makes a small problem and the big problem, right? That's exactly, even with exponential backoff, that's exactly the left paragraph. Like, you had some hiccup, like somewhere things went off, right? And then that problem just repeats itself many, many times, and that's how the big problem the small problem becomes a big often problem. So when we talk about resilient systems and retries, right? Basically, whenever anybody says, "Oh, I'm going to retry," the first question you should ask as an architect, right? Do you have backoff and do you have jitter? Because once this goes into high volume, those are the things that have the best chance of saving your life. The other thing that's important to understand is that backoff doesn't reduce the total load that needs to be processed, right? Everybody is still retrying. So if you have 100,000 clients in the queue who didn't get happily served by your system, they're backing off, but still all 100,000 want to get processed. So, they're becoming a little bit more patient, but the amount of total work doesn't actually go down. So the key thing is, at some point you need them to give up. That's what we call a retry policy, right? You need something where they actually say, you know what, this isn't going to work. Like, it's a little bit like back pressure, right? Where they say, like, look, it's not worth retrying again. So a lot of people who build high-performing systems understand very well that there's a fundamental difference between short outages and long outages. Right, short outages is the spikes. Backoff and jitter tends to work relatively well, right? The thing had a hiccup, right? Everybody who got hit by that window where the hiccup happened, right, tries at different times with exponential backoff, and the system can get itself back into a steady state. If you read a lot of the write-ups or documentations where systems had sort of longer outages, and it doesn't have to be like days or something, right? But it could be like 5 minutes, 10 minutes, an hour, a couple hours, right? Where a lot of work is piled up. The problem that those folks face is the system will not come back up, because that pile has gotten so big, even with backoff, right? Because everybody still wants, right? So that pile has gotten so big that bringing the system back up is extremely difficult, because it's like it scales up and it crushes immediately under the load, because all the load is still there waiting for it. So it's very different system design behavior between short intermittent outages and longer sort of fundamental outages where the system really has to be restarted. You can read a lot of interesting blog posts exactly around this kind of problem. So what do almost all clients do? And I joked a little bit about being synchronous. So here is a synchronous, two words, right? Not asynchronous, but a synchronous interaction model, and that is gRPC. And this is, it's open source. It's really nice. It's out of the client library. You can see, I kind of compressed the code tiny bit, but it's basically all there. I took the error handling out because the font gets too small. But basically, what it does is using kind of sort of like a leaky bucket kind of algorithm for tracking error rates on the retry. So it gives itself a budget for retries, and once that is over, it will actually not try again, right? It's like, is above threshold, on qualified failure, then check is above threshold, right? So it will actually not try again. So what it does is every time a request fails, it sort of deducts from your bank account, right? You can see this on qualified failure decremented, right? The current count minus 1,000. These are percentages. They multiply by 1,000, so they get integer math. So you can basically set this rate between 0 and 1,000, basically between 0 and 1, and then it multiplies by 1,000. You see this in the constructor. So basically, every time something fails, you sort of deplete your account, and then you have to rebuild that account with successful requests. All right, so when a request comes in, right, and it's actually successful, then the thing sort of, starts to build back up. Right, when it falls under the threshold, it says no more retries. So it will get a new request and see if that will go, right? And if it doesn't, it will not even retry. It will just say this request failed. So almost all client libraries, the AWS client library for its regular APIs has the same kind of logic built in. Very, very common, right? And this is basically so that the system, so that basically our rule number 8 doesn't happen, so that retry logic doesn't take the system down by actually increasing the load, because now you don't do things once, you do everything n times because you have the retry. Downside of this, right, there's some interesting logic about this. If you have many different clients, in this case, each client's kind of building their own image of the state of the system. There's no global counter here. Right? So really what you want to limit the global load on the system from all customers. Now that would mean you have a coordinated resource between all customers. If this is a situation where you're dealing with an overload or failure situation in a distributed system, probably you don't want another global resource, which could be a point of bottleneck. So almost all of these systems use a distributed kind of notion. Like it could be, for example, that one client is just particularly unlucky and always gets the failures. They're like, oh my God, this whole system is wrecked. I'm not going to retry at all, versus other people just going through. That stuff can happen. In reality, it turns out that is not the biggest problem. It's generally worth the trade-off, because again, the global coordination would be harder, and just introducing more potential issues into a system that is already struggling. So much about retries. Be careful with retries. They're well intended, but they're like the magic thing to make a small problem into a big problem. It drags the whole system down. And as I said, in many cases, it won't even come back up, because the second anything comes up, all the retry logic is like, oh, look, the system is available. Like, boom, it goes right back down. I have two more, and then I have some bonus ones. The two more, we talk about some favorite topics. It's about order and duplicate messages. I used to work at AWS. Every customer always came like, oh, why can't you deliver my messages in order? And why do I have to deal with duplicate message delivery? This whole distributed asynchronous thing is already difficult enough, and then you're making it even worse for me by, giving me extra stuff to do this. So I have a famous saying that in-order delivery is the thing that architects like, but that the people standing in line don't like. Because in-order delivery is at the supermarket, there's one person in the front who came before you, and they take forever, and you're all waiting, and everybody's like, come on, open another register. Why can't I come in? Let somebody pass, right? If you're in the queue, you will want out of order delivery because you don't want to wait for that person in the front. These are people waiting for baked potatoes, actually. The shop had just opened, is my picture, right? They're very patiently, nicely waiting in line, right? But this is in order delivery. There is no line cutting. So be careful, right? In-order delivery makes your system design and writing the applications, more convenient. It is not necessarily what's good for a distributed system because it includes waiting time. All right, and we have a nice diagram for this. Yeah, my range is a little bit limited here. So what happens, right? If you have A, B, C, D, you have competing consumers. You made a system that can scale out, right? During the break, gentleman made a really good comment where he said, like, if you have an overloaded queue, and we talked about time to live, tail drops and back pressure. The other thing, of course, you could do is increase capacity, right? If you can process more of your queue, right, then the queue doesn't fill up and life is good. So that's what we're doing here, right? We're increasing capacity, competing consumers. But yes, if things have to stay in order and B takes a really long time to process, right? Basically, nobody else can do anything, right, until B is done. And we said earlier, we already observed, waiting is sort of the arch enemy of throughput, right? If stuff is waiting, it's not being put through. So waiting is never a good thing. So if you demand in-order delivery, you're generally hurting throughput because you make things wait. Remember the supermarket, right? If there's one thing in the front, right, and it's very slow, if you guarantee in-order delivery, right, everything has to wait for that. So it's very easy to bring issues into an in-order delivery system. All it takes is one message, right, that doesn't make it through. Now, you could give a timeout, right, time to live and stuff, right? You can make it so that the person can't be at the checkout stand forever. After 5 minutes, you say, okay, fine, like we're done with you, so you can compensate for it. But basically, you make the system more fragile because one thing goes wrong, everything piles up. So be careful what you wish for, right? It's like waiting is the ultimate anti-pattern, and maintaining order implies waiting because, they could be processing C and D, right? But they're not actually happening. So thinking this a little bit further, coming back to the pattern, it was funny. I once gave a talk many years ago somewhere about integration patterns, and somebody asked me a sheepish question. They said, so what do you think of the resequencer pattern? It's one of the 65 enterprise integration patterns. And luckily, I could kind of tell the person was kind of like giggling a tiny bit. And I said, since you're asking so funnily, probably what you're after is that the resequencer pattern is kind of the worst pattern in the enterprise integration patterns, right? Because the whole book is about asynchrony, free flow, high throughput, right? So, just let stuff flow. And the resequencer is like, stuff flows until here, and now the fun stops and everything goes back into proper order. 1, 2, 3, 4, 5. Stateful, waiting, slow. Right? That is the sanction. As I said, basically the only reason we would do this is because something downstream forces us to do this. We would otherwise never want to put a resequencer in. And if we have to do it, we put it as late or as little as possible to minimize this kind of effect. So the problem is with resequencers is, they need to keep track of messages, right? You're missing message, what do we have here? We're missing message 2, right? 1 came, fine, good enough. Then message 3 comes, we're still missing 2. 5 comes, we're still missing 2. Then 2 comes, right? I'm reading the top picture straight from the book, right? You get number 2, and finally number 1 to number 3 can be sort of flushed out, right? But like, how long is this buffer? And it starts to look back like the queue, but a little bit worse, because how are you going to shed things here? Because you might be messing up the sequence, right? It also could be, that doesn't have to be 1, 2, 3, 4, 5 in a way, like it could be consecutive. Well, no, actually it does have to be consecutive, sorry. It has to be consecutive because otherwise he wouldn't know you missing one. So even in the book, and I said many things back then, we were a little bit lucky that we got them right, but even back then we had a feeling, and this picture is also straight out of the book, a little bit 80s style graphics here, the pixel art, right? We always said there's a sort buffer, something throttle, right? Classic back pressure. We didn't call it that at the time, right? But there's also a send buffer and a throttle. Network systems very much work this way because, TCP, different routes, right? Packets go different routes. They can be out of order. They need to be put back in order. It has a certain buffer size, and it tells the sender pretty much the window size. How many messages can you pump in at one time until you get acknowledgement so that even in the worst case, I can get the messages back in order. So if I only have a buffer of 20 messages or 20 packets, right, I tell the sender at most in one, before you get the next acknowledgement, at most you can send 20 messages, because even in the worst case, is the first and the last one I flipped, I can still handle that, and only then do I allow you to send more messages. Classic flow control, and almost every network kind of thing does that. So yes, the resequencer, if it needs to fix the sequence, two problems you have, right? It's like the one thing, it needs an infinite buffer to look for, right? And even if it did, it would take infinitely long to find the missing message, right? Nothing goes downstream. So the downstream consumers will be very unhappy. Like the supermarket will also be unhappy, right? If one person takes forever because everybody's waiting in line, could be spending money, but isn't. So ultimately, this starts to look much more like a database. You need a large database. I also hinted earlier, right, whether things are required to be in order or not is a form of coupling, right? If one system makes an assumption that things gets in order, the other one changes from in order to out of order, that is a change that now propagates, and boom, you have coupling, right? You need to change both sides. Versus if the other system doesn't assume order, right, the sending system can do things in order, out of order. It can change its mind without the other system being affected. So assuming order is a form of coupling because changes will propagate. So what in reality happens, because that's nobody wants to have the system waiting all the time and reducing throughput, is almost all systems reduce the order to a limited scope. They don't put global order on the queue, but they're saying we maintain order in certain shards or logical groupings or partitions. Folks who work with SQS FIFO queues, folks who work with Kafka know this very well, right? Order is guaranteed within a certain scope. It doesn't make the problem completely go away, right? If you say sort of the greenish colored one and the reddish yellow colored one, they're in different groups. They go in different logical FIFO channels. So basically, if B is slow again, right, the next yellow thing will have to wait, right, for this, because C could be done, but it needs to wait. C is basically done, but it needs to wait until B is done to maintain order. But A and D is lucky go happy, they are not affected at all. So almost all systems, because global order is just way too expensive, so almost all systems restrict order. And that makes sense, right? So let's say you have customer updates, and your downstream system cannot do an update before it does an insert of the customer, right? It needs to create the customer before it can update the customer. So if it gets out of order, right, it will be very unhappy. But that is for one customer, right? The other customer, if that happens in the same order or not, is completely irrelevant. So you will have these grouping IDs like your custom IDs, entity IDs in your domain model, right? So that within one entity you maintain order, and you don't need to try, or you don't try to maintain global order. So most of the systems that you will find, almost all of them have this, and the worst thing you can do is put the global order in, right? If one thing gets stuck, everything is basically stopped, not what you want, right? So basically, this reduces the waiting time, and it's usually done by some domain entity, this kind of split, because they're generally logical channels or logical partitions, so making more of these is not such a big problem. So if you look at a few footnotes, so here's from real systems, right? So SQS, Amazon Simple Queuing Service has FIFO queues, right? But because it's an operationally stable, high-volume system, even here, we were joking during the break a little bit, right? The people who work with these kind of systems in the cloud, they usually know this stuff because they stumbled across all the problems and ended up reading the documentation very, very carefully, you will see stuff like this. This is straight out of the documentation. There's a maximum of 20,000 in-flight messages that you can have on a FIFO queue. So basically, and this goes across the queue. So if you have a backlog of messages in a single message group, you cannot consume messages from other message groups. So it is not completely decoupled, right? So again, like the global order thing doesn't work well, and it says, hey, I give you all these groups, but be careful. If the groups get completely out of whack, if one never wants to if one is backed up by 20,000, you're done, right? Because I'm not willing to give you that much look behind, like the sequencer, right? In the end, like basically, if you need this, the short answer is you should have used a database and not a queue. Right? This is like, if you want this, right? Like, let's just make it like basically, don't make me do things in order, right? If you cannot keep that kind of order, right? Kafka does this with partitions, very commonly used, right? It's often done by a key, like it hashes, the incoming messages. So messages with the same key go on the same partition, right? Because the hash is predictable. The cache thing, the catch is always, is this evenly distributed? You could have things that overload one partition versus another, and you need to deal with this. So even there, it isn't like sort of magically, hey, just like put order into the system, and I don't want to worry about it. As soon as you put order into these kind of systems, you have more stuff to deal with, and read footnotes. I think the Kafka documentation says something, this could be a problem, but there are ways to deal with it. And then, read on, basically. So almost everybody puts a limitation on the scope of the order. So last one here, minus the bonus ones. And I already hinted, like in the end, if you want these kind of things exactly once, if you want in order, essentially what you're asking to do is like, you're not really wanting a queue. You're not really wanting an asynchronous parallel kind of system, because asynchronous parallel kind of systems tend to have parallel processing. They put things out of order, right? And they will also inherently duplicate a message. Why will they duplicate messages? Well, the classic scenario is this: competing consumers, message A gets processed successfully, everything is fine. Then message B comes, and message B is not as fine. And the question is, what do you actually want to happen? So in many cases, you actually want a duplicate message, right? Because the processing of the message didn't succeed. Now, the yellow box isn't a single step, so some pieces might have happened, right? And then something went wrong later, so the message couldn't be processed completely. Now you probably do want the message again, so you're gonna do some things again. It's almost unavoidable. You can't just sit there and say, hey, I don't want to have duplicate messages, right? Because in error handling, almost invariably, you will have to face this. So almost all the queues, what they deal is they have this limited visibility timeout. Actually, friends of mine wrote the book, The Cloud Computing Patterns, so it's actually very nicely described in there as a timeout-based delivery. So the way the systems deal with this, and SQS does this, I'm sure GCP pops up, they basically all work very similarly, is that the message is put on a bus, it is made visible, then the receiver reads the message, and the message is no longer visible to other consumers, but not deleted, right? It's just invisible because it's waiting for this acknowledgement. And then once the acknowledgement comes that, yes, the processing was successful, then the message is removed. And if the acknowledgement doesn't come within a certain timeout, it will go back to sort of number 2 and make the message back visible again. So this is, SQS very, very much works like this as, visibility timer. So then the message is back there, right? It's like, boom, right there you have a duplicate message in a way, right? Because it was processed, but not 100%, but we don't know how far. So in the end, you can't really have exactly once delivery. So what do you do instead, right? You make things item potent, right? So that when it's done multiple times, it behaves as if it was done a single time. And there's sort of two ways to do this, and hence my learning, right? Either you track every message that you received in a database and you say, hey, did I already receive this thing? If yes, then don't do it anymore. And that's why in the end your system starts looking a lot more like a database than a queue, right? Because you always, everything goes in the database anyhow. You're sort of wondering, why don't I just write into the database, right? Why do I even have this queue? A little bit more elegant way, which sometimes works, is make the semantics of your operation inherently idempotent. So basically insert versus update is not idempotent, because if I insert twice, so I probably get an error because I already have it, or if I lost the insert message, whatever it is. So having a put operation, which many NoSQL databases do, like DynamoDB, I don't want to say a put. Basically, if the entity doesn't exist, it will create the entity, and if it already exists, it will update it. So if you do this twice, you get the same result. Need to still be careful with out of order, right? Because you might be overwriting other changes, and that was number 9. But basically, in number 10 is, if you can make things inherently idempotent, that is definitely a good way of dealing with it. The funny thing is, most of the time, that is if there is a database behind, right? Because if you need to remember if you did something before, it means you need to keep state. Where do you keep the state? Mostly in a database. So you do that explicitly or implicitly. Yeah, and you might have the same questions. How much look behind do you want to have, right? If you got the same message like 5 years ago, do you still want to detect, right, that was a duplicate message? Maybe not. So you auto-purge. You give limited time to live to the data you put in the database. So you purge all items. Basically, everything that has global order, global state, you end up time limiting. As I said, even the cloud providers do it. They say, hey, 20,000 you get, at some point it's just over, because the kind of system you're trying to build is an asynchronous free-flow kind of system. So if you're trying to put global deduping and global order back in, ultimately there's a limit to how much I'm willing to put up with, because it will no longer give you the properties of the kind of system that you wanted to build. Well, we still have a tiny bit of time, so we get some bonus truths. I was tempted to make the whole session called Event-Driven Architectures, because I figured twice that many people would show up. But that would be unfair, so now it's a bonus for folks who came anyhow. Get a little bit about event-driven architectures, right? So a lot of things, and we joked about this just during the break, where people say, oh, I use events, I'm loosely coupled. Right? Sort of, and you, like, as an architect, we said, these blanket statements should make you suspicious, like it's always like this and never like this. Oh, I do this, so I'm automatically, decoupled or loosely coupled. As architects, we can look a little bit more closely. So what does event-driven architecture actually decouple? And what we'll find, in most cases, it decouples additions, but it doesn't decouple changes. So first, my little soapbox. So there must be a tiny bit of an advantage I have by standing down here and you guys sitting comfortably up there. So I get to have my little soapbox, and I declare that events are just messages. And the best fact to fall back onto that I have is, well, Bobby and I wrote this down 20 years ago and nobody complained, so it must be true. So events are messages. They're not like a different thing. Some people say, oh, it's messaging versus eventing, and like, no. The messaging is the interaction style. Messaging says that it's asynchronous. The thing gets into this data structure called a message. That gets transported from A to B, and then B does something with it. That is messaging. What that message represents, that is the semantics. It could be a command, it could be a document, or it could be an event. So two different things. One is the interaction style, the other one is the semantics of a message. That's why an event is a message, because it uses messaging as the interaction style, right? It goes through queues, it goes through event routers, it does all the same things that messages do. So when we talk about events, it's actually quite interesting to think about, how do I name this channel, right? If I want something to go from A to B, and we have the ability to decouple by putting a channel in between, what should this channel be called, right? And again, there's some choices. Maybe some you might say, okay, they're obviously not great, but still you have some choices. They're all reasonable. You could call the channel the same thing as the recipient. It was saying, I didn't really get location decoupling because the credit service channel is the credit service. On the other hand, it makes the system easy to understand. You know who A is talking to. If something is broken, right, you know where this message went. Rather than having the name of the service, I could have the name of the action. Well, I need to verify the credit card. Well, yeah, I don't care who does that. Maybe the credit service, maybe somebody else, right? But I have a clear command pattern, right? I can also send a document. Here's like payment information. And now the right-hand side needs to know that the appropriate action for payment information is to validate that information. So it's not like you're magically making the coupling go away. You're shifting a little bit of the burden from the left to the right. And the last one, right, is like order is placed or order is received, right? Still the connection has to happen somehow. There's no magic here, right? The right-hand side needs to know that, the credit service needs to know that when an order is received, I look at the payment info and I validate the payment info. So the connection must be made. You're just shifting a little bit from how much does the left-hand side prescribe what happens versus how much does the right-hand side describe what happens. Like you're shifting this, but you're not magically making it go away. So that's the first insight here. It's like little nuances, but there's no magic of things that like decouple, right? Either one side or the other side has to say what talks to what. Now, there is a dimension of coupling where you can play with, and a lot of event-driven systems do this, or subsystems do is like, well, how do the two find each other, right? So the one is by the name of the channel, right? So they know they talk to each other at channel name. So that's the first one, right? So if an order is received, I know I need to validate the payment information. So I read from that order received channel and I know what to do, right? That's where the connection is being made. Many pub subsystems have, more intricate mechanisms where you could say they're more loosely coupled. I would be a little bit careful with the word, but they're definitely more flexible by having topic hierarchies. So it's not like one channel does one thing, but you have a hierarchy of things like, this could be orders for new customers placed in Europe, or what do I have? This is an online order, a new online order versus an updated online order. You have this kind of hierarchy. TIBCO did this a lot, right? When we wrote enterprise integration patterns, was these topics were nested. JMS, I think, does that also. Funnily, the AWS services do it without ever saying it because they have prefix matching. So if you have a proper notation, right, if the dots cannot appear, if this is orders.online.new and the dot is a special character that you cannot use, prefix matching will allow you to subscribe to the leaf as well as to a higher node. So you can actually do this with EventBridge just with string prefix matching. It might seem a little clunky, but totally gets the job done. And the last one is just doing it based on fields. Any message that has a credit card number in it, I want to go and validate that credit card number and make sure that's a valid number and that I can do a token transaction against that, right? I just do it purely by content. So I can play with like where the connection has to be made somewhere. So I can either do it by channel very explicitly, I can do it by hierarchy, gives me more expressiveness, or I can do it by content. Trade-offs here are similar. The systems on the top are a bit more rigid, but easier to debug. All right, the bottom system, right, you would have each message could be going to a completely different place. So if something isn't working properly, right, it's harder to know where to look, right? The same old trade-off that we discussed in many other parts. So the one thing, and we just chatted about this in a break a tiny bit, is when people say event-driven things are more loosely coupled, we need to distinguish between what comes from the pub sub-channel versus what actually comes from calling the event, the message an event, right? If I change my verify credit card to order placed, nothing really happened in the system, right? I just changed the name from A to B. It could be foo and bar. So changing the message name from foo to bar is unlikely to do magical things to my system. Most of the properties that people talk about when they talk about event-driven architectures come from the fact that they commonly use publish subscribe channels, like Kafka will do or SNS will do, right? And what publish subscribe channels allow you to do is they make adding recipients decoupled from the sender. The sender will not know how many recipients you have, because if you have a publish subscribe channel in between, you can add more recipients and the sender doesn't need to change. So the system becomes decoupled or more loosely coupled towards adding more recipients. We always said when we say coupling, we need to say the dimension. So this is the dimension of topology, and very specifically, intermediate, same thing. Messaging, you can insert intermediates as much as with PubSub and eventing, right? No difference. The thing is adding recipients, right, who each get a copy of the message. That becomes side effect free. So that's often what people rely on. So it's not so much the event semantics, but it is the PubSub. If I PubSub broadcast my verify order, and one part of verifying order is verifying the credit card, and another thing is verifying the address, and another thing is verifying inventory, that is totally fine. I stick it on a PubSub channel, right? The message goes to the respective recipients, which all subscribe, right? There's, as I said, changing something from food to bar isn't gonna change the characteristics of your system, but putting a PubSub channel in does. So a lot of the event-driven benefits people talk about come from the fact that it's a PubSub channel, not so much from the fact that it's an event. So and here's the key thing, right, is basically a PubSub channel, this adding a recipient, the subscribing stays within the channel and the sender doesn't need to know. Versus if I have a recipient list, right, where the sender knows I need to send the message for the following 3 recipients and now it's 4, right, that change trickled through. But careful, the sending of the message and any changes to the message format affects all the recipients just as much as before. So changing the event schema now is totally coupled, right? Because that's no different, right? If I have a different field or take one away or add one, right? That left to right, right? This changing the message trickles through to the recipients just as much before. So these PubSub event-driven things work very well in situations where the schema changes rarely, and by design, the sender doesn't want to know about all the recipients. So infrastructure is very much like this. So actually, some of you may know, so EventBridge, right? AWS EventBridge was originally a systems management tool. It wasn't an integration tool. It was called CloudWatch Events, I think it was called CloudWatch something. It was part of CloudWatch because if the cloud infrastructure, in this case AWS, right, could be anywhere, if the CloudWatch infrastructure wants to notify you of stuff happening, by definition, AWS doesn't want to make a change when you subscribe to this event, right? Makes no sense. And also these events are extremely stable, so this event-driven stuff works very, very well, right? Anybody could subscribe to, hey, something got added to this S3 bucket, or some Lambda function had an issue and needs to restart. Anybody can subscribe to these events. The left-hand side never has to change, and the schema is very unlikely to change because these events are very stable. So then this actually works, but there's no magic here. So the one thing you also find that the more you add, because adding is easy, the trickier the other coupling comes, right? If you have 1,000 recipients, because you made adding so easy, if you do change the event format, you now have, change propagation, you have coupling to 1,000 recipients. So these things often do well for adding, they don't do as well for changes. Right? So adding recipient, right, that's where the event-driven architectures gain, but sort of format or semantic changes, they don't. So if you use too much of the top and add too many subscribers because it's so easy, you kind of gain there, but you lose below, right? And that is actually risky. Doesn't mean they're bad, but it means as architects, right, we have a much more nuanced view of these kind of things rather than just running around, hey, I use events, so I must be cool, and it's loosely coupled. Very last one, and I promise this one is a short one, is, I hinted at this at a slide earlier, is be really careful. A lot of these systems have very nice architectural properties like decoupling, change tolerant, self-healing, resilient, anti-fragile. Like, this is stuff that we want and we like as architects, and well, as users, we like them also, right? Because these systems run really nicely. But the one thing you need to be really careful is that if you do too much of this, if you want to decouple everything from everything, and everything is asynchronous all the time, and with many intermediaries and this and that, and it's routed based on field values, the system you're making is more complex. And as we saw earlier, developer tooling is often less available, so this architect's dreams by ticking all the boxes might make it very inefficient of working against these. And you even see this with some of the cloud systems, right? It's like calling a method locally, like you never think about it. You can do 1,000 of those in an hour. If you suddenly do this in an asynchronous distributed system, even with serverless, right, field formats, the JSON path expression isn't quite right, you didn't set the permissions right, productivity does go down. It takes longer to wire two Lambda functions together with SQS than it takes to make a method call. Such is life, right? So use it wisely. Use it where you really get the benefits, but don't use it where you don't, right? So because the architect is going to be happy, right? This is all things that you want. Developer might not be nearly as happy because, it's easily composable, but hey, if I don't know what talks to what, how do I refactor this? I have no tooling support. How do I know all the recipients? Can I actually ever change a message? Nobody knows, right? Queues are filling up, all that kind of stuff. So both the developer and the ops folks, right, might not be as happy as you are on paper in the system design. So I always remind people, right, this is a toolkit. This is not a requirement that should be using all of these kind of things. Remember the poor architects saying, always do this. No, you don't need to always have a queue. You don't need to break everything down into tiny micro modules of everything. You don't need asynchronous all the time. You don't need self-healing and auto-scaling all the time, right? It's good to know all these mechanisms, but remember the chef, right? More important is knowing how to put it together. When do I want which thing, and when am I better not doing it? So I did want to give you that bonus advice because I have seen this happening, right? Where the architect thing is the fantastic thing, and then somebody asks, well, why does it take forever to build anything? Well, exactly for the same reason, and you're not making anybody happy, right? So basically what you're doing is you're shifting flexibility to the runtime, right? You have more possibilities to change the system later, and that's cool, right? Because you don't need to go back and recode your system to add another recipient or to change something or put intermediate, right? You can do more things in the runtime. You push things downstream, but it also means you need more tooling support. You need more safety net, right? The downstream now has a lot more flexibility, so also a lot more opportunities to shoot yourself in the foot, right? So you need to be better prepared on this. Maybe have better observability. Probably you need better documentation. And yes, some of these ideas are not very new. Back in 2007, I gave a series of talks like 17 years ago about, that's why the graphics look a little bit funny, Internet Explorer, yeah, very cool. Flashbacks here, where we said, hey, I put things into a channel, but nobody ever reads from this channel. Will somebody tell me? I can tell you, a normal cloud infrastructure will not, right? Okay, perfectly cool system, right? Except it doesn't do anything, right? It's like, doesn't function. So what we built was tools that build the system dependency graph and warns you of things like you have a tight loop. Maybe that's not what you wanted. Oh, you're writing to this channel, nobody actually reads from this channel. So these things you now do want to know, because you push this downstream, you also need more tooling downstream. So hopefully you enjoyed the 10 truths of distributed computing, right? What we learned is that the enterprise integration patterns did a good job at talking about the what, the message formats, the routing, the transformations, the filtering, the claim checks, all this kind of stuff, right? That is a design-based activity, and almost everything we talked about today right, is the how. Who pushes, who pulls, what is, the flow control mechanism? Is this back pressure? Is this tail drops? Is it time to live, right? How about in order, out of order? Do I need to? Can I accommodate out of order, right? That is all about the how. And as I mentioned, this is fresh content, so my plan is to turn this into a proper series of videos, and also hopefully write a small book about this and document this as a new set of patterns, or maybe at least a set of truths, so we can also help distributed system designers not only think about the top part, but also equally much think about the bottom part. If you like this kind of stuff, the enterprise integration pattern side is old, right? It's as old as the book. That's why it sometimes looks funny, but it's not dead. It's just dormant. So every couple of years, new stuff comes. So there's quite a few new blog posts, many of them around serverless and serverless automation, but the most recent ones have quite a bit more depth around, right? You recognize some of these kind of thingies, right? So be welcome. This is all freely available, so you can read up more around this flow control flow. This is enterpriseintegrationpatterns.com. Ping me on LinkedIn. Just don't comment on the looks of the website. I do know it looks classic by now. That is actually a feature. And with that, that's all I had to share for today. So thank you so much for your attention.